Look up at the night sky, and you might think you understand what you're seeing: pinpricks of light, steady and eternal, following rules written billions of years ago. But what if I told you that the universe loves breaking its own rules? That out there, hidden among the familiar constellations, are stars so bizarre, so defiant of the laws of physics, that they've left astronomers utterly speechless. These aren't just unusual stars, they're cosmic anomalies, celestial rebels that shine in ways they simply shouldn't, existing in places they have no right to be, and behaving in manners that upend everything we thought we knew about how stars live, die, and shape the cosmos. Imagine a universe where stars come back from the dead, where suns race across galaxies like runaway trains, where diamonds the size of planets drift in atmospheres of pure carbon. These aren't scenes from science fiction, they're real discoveries, each one a profound mystery that challenges our very understanding of reality. What if everything we thought we knew about stars was wrong? What if the textbooks are filled with more questions than answers? These stellar enigmas aren't just curiosities. They're forcing us to rewrite the rules of stellar evolution, to question the fundamental principles that govern matter, energy, and time itself. They remind us that the universe is far stranger, more dynamic, and more creative than we ever dared to imagine. In this video, we're going to journey through the cosmos to meet these magnificent rule breakers, stars that glow with impossible light, spin at unimaginable speeds, and harbor secrets that could redefine physics as we know it. From zombie stars that cheat death to ancient suns older than the universe itself, each one of these celestial marvels tells a story of curiosity, discovery, and the endless wonder of exploration. So join me as we unravel these cosmic puzzles, and together, let's rediscover the night sky not as a static painting, but as a living, breathing, and astonishingly mysterious universe waiting to be understood. And so we arrive at our first cosmic paradox, a stellar phenomenon so unsettling it earned the nickname zombie star. Picture a star that has already met its cataclysmic end in a supernova explosion, a titanic blast that should have left nothing behind but an expanding cloud of debris. Now imagine that somehow, against every known law of stellar physics, that star isn't completely gone. A fragment of it remains, not only surviving the blast but actually reigniting, shining once more in the void. This isn't science fiction, it's a genuine, observed anomaly that has astronomers both fascinated and deeply perplexed. The story of their discovery begins with a supernova that just didn't follow the rules. Astronomers rely on a specific class of stellar explosion, known as a Type Ia supernova, as a standard candle. These events occur in binary systems where a dense white dwarf siphons material from a companion star. Once it reaches a critical mass, a runaway thermonuclear reaction tears it apart in a brilliantly predictable explosion. The light curve, the way its brightness changes over time, is so uniform that scientists use it to measure vast cosmic distances. That is, until they found ones that weren't so standard. Researchers poring over data from automated sky surveys noticed something odd, a supernova that flared up but then didn't fade away as expected. Instead of dimming into obscurity, the light persisted, hinting that the heart of the star was still beating. This is where the real detective work begins. Astrophysicists have proposed several theories to explain how a star could cheat death so spectacularly. One leading idea is a partial detonation. In this scenario, the white dwarf does explode, but the explosion fails to consume the entire star. It's like a firework that fizzles only halfway, leaving a chunk of the core intact. This surviving remnant, now heated and shocked by the blast, could then begin nuclear burning again, effectively coming back to life. Another compelling theory involves the violent merger of two white dwarfs. As they spiral into each other, the collision could trigger an explosion on one of them, while the other is sent hurtling away, wounded but not destroyed, its composition altered in a way that allows it to start shining anew. We don't have to look far for concrete examples. Take supernova 2012Z, a prime case study in this bizarre behavior. Located in a galaxy roughly 110 million light-years away, this event was initially classified as a standard type Ia supernova. But then it started acting strangely. Its light curve was unusual, and follow-up observations with the Hubble Space Telescope revealed the true shocker. The star that exploded was still there. It had survived. The pre-explosion star was actually a white dwarf in a binary system, and post-explosion, the system was still visible, though dramatically changed. The surviving star was now brighter, hotter, and utterly transformed, a true phoenix risen from its own ashes. The implications of these zombie stars ripple far beyond mere curiosity. For decades, Type Ia supernova have been the bedrock of cosmology, the key tool used to discover the accelerating expansion of the universe and the existence of dark energy. That entire edifice is built on the assumption that these explosions are consistent and predictable. The discovery that some of them are not, that some might be failed or partial explosions, introduces a potential source of error into our most precise cosmic measurements. It forces scientists to go back and recalibrate their models, to question if our understanding of these cosmic mileposts is as solid as we thought. It's a humbling reminder that the universe is always more complex than our textbooks. So what does this mean for our grasp of cosmic rules? If a star can endure its own funeral pyre, what other fundamental truths might be more flexible than we imagine? The existence of zombie stars tears a small but significant hole in the fabric of our stellar understanding, a hole through which we can glimpse an even stranger and more dynamic universe than we ever anticipated. It sets the stage for phenomena that are not just unusual but seemingly impossible. But if a star-cheating death feels like a cosmic horror story, our next anomaly is more like a high-speed thriller. Imagine a star not just enduring, but escaping, breaking free from the gravitational chains of its entire galaxy to become a lone wanderer in the intergalactic void. These are the hypervelocity stars, cosmic runaways hurtling through space at speeds so immense they can reach nearly 2 million miles per hour. To put that in perspective, at that velocity, you could travel from Earth to the Moon in under 15 minutes. They are the ultimate expression of stellar wanderlust, and their discovery was almost as dramatic as their journey. The first of these stellar speedsters was found not by a targeted search, but entirely by accident. In 2005, astronomers sifting through data from the Sloan Digital Sky Survey noticed something peculiar about a star catalogued as SDSSJ 090745.0 plus 024507. Its spectrum indicated it was a hot blue star, but its motion was all wrong. While virtually every other star in the Milky Way orbits the galactic center in a relatively orderly dance, this one was different. It was moving at a staggering 850 kilometers per second, almost 3 times the velocity needed to escape our galaxy's gravitational pull. It wasn't just leaving the neighborhood, it was on a one-way trip into the emptiness between galaxies. Astronomer Warren Brown, who led the team, described these objects as stellar cannonballs, a name that perfectly captures their violent origin and incredible speed. So how does a star get kicked out of its home with such ferocious energy? The most widely accepted theory points a finger directly at the supermassive black hole lurking at the very heart of our galaxy, Sagittarius A star. The physics involves a kind of cosmic slingshot, but one that requires a tragic sacrifice. The scenario begins with a binary star system, two stars orbiting each other, that wanders too close to the monstrous black hole. The immense tidal forces of the black hole violently disrupt the binary's orbit. In a gravitational game of cosmic pinball, one star is captured by the black hole, swinging around it in a tight orbit. The conservation of energy and momentum dictates that the other star must be flung away in the opposite direction at an enormous velocity, ejected from the galaxy entirely. It's a three-body interaction where the black hole acts as the ultimate particle accelerator, sacrificing one star to launch another into the abyss. While the black hole slingshot is the leading explanation, it's not the only way a star can achieve such extreme speeds. Other mechanisms can produce these runaway stars, though typically at lower velocities. Close encounters in dense star clusters can fling stars outward through gravitational interactions. There's also the possibility of a supernova explosion in a binary system. If one star explodes, the sudden loss of mass can release its companion like a snapped tether, sending it flying off into space. However, the incredible velocities of the fastest hypervelocity stars, like the famous Strangest star, point overwhelmingly to the immense power of a supermassive black hole as the primary accelerator. These stars are unique tracers, their paths across the sky acting as forensic evidence of a violent encounter that occurred millions of years ago. Tracking these stellar cannonballs does more than just satisfy our curiosity about cosmic escapees. It provides scientists with a powerful tool for mapping the invisible. The trajectory of a hypervelocity star is dictated by the gravitational field of the entire Milky Way. By meticulously measuring its path and speed, astronomers can essentially work backwards to chart the distribution of mass in our galaxy, including the vast, unseen halo of dark matter that makes up the majority of its weight. Each one is a probe sent on a mission, unintentionally mapping the gravitational landscape of its home as it flees. It's a perfect example of how the universe's greatest oddities often become its most valuable tools for discovery. One can't help but be struck by the profound loneliness of their journey. Picture a star like S5 HVS1, another recently discovered hypervelocity star racing through the silent darkness. For eons, it will travel through the near-perfect vacuum of intergalactic space, its light a solitary beacon in a sea of black. It will never again be part of a galaxy, never have planets, and will eventually fade away as it cools, a ghost of its former brilliant self. Its entire existence is defined by a single, catastrophic event millions of years in its past, a moment of violence that set it on an eternal, isolated path. This stark reality shifts our focus from stars that are merely fast to those that exist in places we once thought were utterly inhospitable to star formation altogether. Just when you thought the cosmos couldn't get any stranger, we journey from stars fleeing their homes to stars being born in places that should be cosmic dead zones. The rules of star formation seem simple enough. You need a quiet, dense, and cold cloud of gas and dust where gravity can slowly work its magic, pulling material together until a new sun ignites. It's a delicate process, one that requires a certain cosmic serenity. So, imagine the sheer astonishment when astronomers pointed their telescopes toward the most chaotic, violent, and destructive environment in our entire galaxy. The immediate vicinity of the supermassive black hole at the Milky Way's core, and found not just stars but young, brilliant, massive stars. It's the equivalent of finding a thriving, vibrant nursery in the middle of an active volcano. This discovery didn't just break the rules, it threw the entire rulebook into the black hole itself. For decades, the region around Sagittarius, a star, our galaxy's central supermassive black hole, was thought to be a place of pure destruction. The tidal forces there are so unimaginably powerful that they should shred any molecular cloud long before it could possibly collapse into a star. The environment is bathed in intense ultraviolet radiation and searing X-rays, which should heat and dissipate any potential stellar building blocks. Everything we knew about physics said that this was the last place in the universe you would ever expect a star to be born. And yet, there they are. Orbiting perilously close to the event horizon is a population of young, massive blue stars known as the S-stars. Their very existence is a paradox that has forced astrophysicists to completely rethink how stars can come into being. So how do you make a star in a place where star formation is forbidden? Experts have proposed some incredibly ingenious, if not outright wild, mechanisms. One leading theory suggests that the very force we thought would prevent star birth, the black hole's immense gravity, might actually enable it. A massive, wandering gas cloud could be compressed not by its own gravity, but by the tidal force of the black hole as it's pulled inward. This sudden, violent compression could trigger a rapid, almost frantic, collapse of the cloud, essentially forcing it to form stars in a blink of a cosmic eye. It's a top-down process where external chaos creates order, rather than the slow, bottom-up collapse we see in galactic nurseries. Other theorists speculate that these stars might not have formed in place at all, but were instead born in a dense star cluster that migrated inward and was then torn apart by the black hole's gravity, leaving these few brave survivors on their precarious orbits. The challenges these stellar rebels pose to established theory cannot be overstated. Our classic models of star formation are built on the assumption of a relatively calm and isolated environment. Finding vibrant young stars in the galactic equivalent of a war zone means those models are, at best, incomplete. It tells us that the universe has more than one way to create a star, and some of those ways are far more dramatic and extreme than we ever dreamed. This isn't just an academic curiosity. It forces us to ask where else this might be happening. Could the furious environments around other galactic nuclei be secretly birthing stars as well? The discovery opens up a whole new frontier of chaotic, extreme star formation that we are only just beginning to explore. The paradox isn't limited to the galactic center. The Hubble Space Telescope has performed deep surveys of what appear to be vast, empty regions of space between galaxies, areas known as galactic voids. These are deserts on a cosmic scale, with so little matter that forming a star should be virtually impossible. And yet, Hubble has occasionally spotted the unmistakable glow of isolated, massive blue stars drifting in these nothingnesses. These lone wanderers are even more mysterious than the S-stars. Did they form there against all odds from some tiny, unseen wisp of gas? Or were they, like the hypervelocity stars we discussed earlier, ejected from their home galaxies at such high speeds that they now travel through the void, their origins forever a mystery? Each one is a profound puzzle. One can't help but indulge in a truly captivating thought. If a star can exist and even form in such an hostile environment, could it host planets? And if it could, what would life be like on a world orbiting a star next to a supermassive black hole? The sky would be a spectacle beyond imagination, filled with the eerie glow of accelerated matter and distorted light, but it would also be a life constantly on the brink. The radiation would be intense, and the gravitational tides would create a world of possibly global seismic activity. It's a reminder that the universe's capacity for surprise extends to the very possibility of life itself, existing in niches we would never have thought to look. This revelation perfectly sets the stage for our next category of cosmic oddity, because if stars can exist where they shouldn't, then surely some must be made of stuff that seems equally impossible. Now, let's shift our gaze from stars born in chaos to stars that are quite literally cosmic jewelers, crafting diamonds on an unimaginable scale. If the previous anomalies were about location and behavior, this one is about composition, a fundamental rewriting of what a star is even made of. We are entering the realm of the carbon stars, celestial objects so fantastically rich in this element that their very atmospheres become factories for stardust and just maybe diamonds. It's a concept that sounds like it's lifted from a fairy tale, a star that could be scattering diamonds across the galaxy. The story of their discovery begins not with a telescope image, but with a spectrum, the unique fingerprint of light that reveals a star's chemical composition. In the late 19th century, astronomers like Antonia Maury and Annie Jump Cannon were meticulously classifying stars based on their spectral lines. Most stars showed strong lines for elements like hydrogen and helium, and crucially, oxygen, but a curious few displayed something entirely different. Instead of the expected signatures, their light was being absorbed by molecules like carbon monoxide and cyanogen, and they showed a startling abundance of pure carbon. These weren't just slightly different stars, they were a whole new class of object with atmospheres where carbon atoms outnumbered oxygen atoms. For the first time, we had found stars that weren't just made of the universal cosmic soup, but were specialized, element-rich wonders. Dr. Emily Levesque, an astronomer who studies these giants, often describes them as the universe's primary carbon producers, the factories that forge the very element that life on Earth is based on. So how does a star become so carbon-enriched? The process is a beautiful and violent dance of stellar evolution. It begins with a star not too different from our Sun, but slightly more massive, reaching the end of its life. After burning through the hydrogen in its core, it swells dramatically into a red giant, entering what's known as the asymptotic giant branch phase. Deep within its searing heart, a process called nucleosynthesis is underway. Helium atoms are being fused into carbon. Then, in a crucial step, the star's own internal dynamics take over. Powerful convection currents, like a colossal boiling pot, stir the star's interior. These currents dredge up the newly forged carbon from the core and carry it all the way to the surface, polluting the star's outer atmosphere. Over thousands of years, the surface becomes so saturated with carbon that it fundamentally changes the star's appearance and chemistry. The oxygen that is present quickly binds with carbon to form carbon monoxide, locking away the oxygen and allowing excess carbon to form other molecules, creating a sooty, carbon-rich atmosphere. This unique composition gives carbon stars their unmistakable and hauntingly beautiful characteristics. To our eyes, they appear a deep, bloody red, far redder than even typical red giants. This is because the vast quantities of carbon in their outer layers act like a cosmic filter, absorbing blue and green light and allowing only the reddest wavelengths to escape. They are also incredibly bright in the infrared part of the spectrum, as their thick, dusty envelopes, rich in carbon compounds, radiate heat. In fact, some of the most well-known carbon stars are surrounded by vast, opaque shells of carbon-rich dust, like the star's own sooty shroud, which are steadily blown into space by intense stellar winds. To truly appreciate these stars, we need only look to one of the most famous examples, CW Leonis, also known as IRC plus 10216. Located about 400 light-years away, it is the brightest carbon star in our infrared sky. It's a pulsating variable star, rhythmically brightening and dimming as it nears the end of its life. Most fascinatingly, it is losing mass at a phenomenal rate, ejecting a thick cloak of gas and dust into space at nearly 30,000 kilometers per hour. Within this expelled material, conditions are just right for carbon atoms to link up and form microscopic particles of graphite, and according to some astrophysical models, even diamond dust. Studies of CW Leonis have been instrumental in helping us understand these powerful stellar winds and the complex chemistry that occurs around dying stars. There's a wonderful historical anecdote that highlights just how strange these objects appeared to early astronomers. Their spectra were so unusual, filled with the strong bands of carbon molecules, that they were utterly unfamiliar. In an era before modern astrophysics, some astronomers initially speculated that these bizarre spectral signatures might not be from stars at all, but perhaps from some new, peculiar type of distant galaxy or nebula. It was only through painstaking analysis that the truth was revealed. They were indeed individual stars, but of a type so chemically peculiar they challenged the very classification system. This brings us to a profoundly humbling and personal thought. Every single carbon atom in your body, the very foundation of your organic being, was once forged in the heart of a star. But not just any star. It was likely created in the final fiery stages of a star, much like the ones we've just described. A carbon-rich giant manufactured these elements in its core and then, through those immense stellar winds, sprayed them out across the galaxy. That material drifted for eons, eventually mixing with other gases and dust to form new stars, new planets, and ultimately, us. We are, in the most literal sense, stardust. And a significant portion of that stardust was once the atmosphere of a dying, crimson-colored carbon star. This incredible journey from a stellar furnace to a living, thinking being is perhaps the greatest story the cosmos has to tell. It also forces us to confront an even more extreme and dense reality, because if a star can be made of diamond-making material, what happens when matter is compressed to its absolute limit? Yet the true terror of a black widow pulsar isn't just its destructive power, but its incredible efficiency. These cosmic predators are masters of a gruesome form of energy conversion. The material they strip from their companion doesn't just vanish. It's funneled by powerful magnetic fields onto the pulsar's surface at nearly the speed of light. This accretion of matter actually transfers angular momentum to the pulsar, causing it to spin faster and faster. It's a monstrous feedback loop. The act of consuming its partner makes the pulsar's deadly wind even more intense, which in turn allows it to devour more material, spinning up even further. Astronomer Roger Romani, who has studied these systems for decades, describes it as the ultimate cosmic vampire, a creature that feeds on its victim to become stronger and more lethal. This process can accelerate these neutron stars to dizzying rotational speeds, some spinning hundreds of times per second, making them among the most precise clocks in the universe, even as they commit stellar murder. Detecting these elusive killers is a monumental challenge that pushes our observational capabilities to their absolute limit. They are often discovered not by their visible light, but by their high-energy emissions. Space telescopes like NASA's Fermi Gamma Ray Space Telescope scan the skies for the telltale signature of pulsars, precisely timed pulses of gamma rays. When astronomers noticed that some of these gamma-ray pulsars also exhibited strange eclipses or showed evidence of a faint, heated companion in optical wavelengths, the pieces of the puzzle began to fall into place. The pulsar's beam itself is often pointed away from Earth, but its destructive wind is omnidirectional, making the secondary effects of its carnage the primary way we find them. It's a classic case of cosmic forensics. We often discover the crime by finding the evidence of the victim first, a faint, dying star locked in a lethal embrace with an invisible, spinning monster. Perhaps the most famous and defining example of this entire class is the original Black Widow itself, PSRB 1957+20. Discovered in the late 1980s, this millisecond pulsar, located roughly 6,500 light-years away in the constellation Sagittarius, provided the archetype for this gruesome behavior. Observations revealed it had a very low-mass stellar companion, a brown dwarf or a planet-sized object that was being relentlessly blasted by the pulsar's radiation. The companion is so close that it completes an orbit in just under 9 hours, and it is so thoroughly cooked that its surface temperature is heated to over 10,000 degrees Celsius, vastly hotter than a star of its mass has any right to be. This system paints a clear picture of the beginning of the end of this binary relationship, showing us the process of evaporation in terrifying detail. The ultimate fate of these systems is as fascinating as it is bleak. Over hundreds of millions of years, the pulsar's wind will continue to ablate the companion, stripping it layer by layer. Eventually, the entire star may be completely evaporated, leaving behind nothing but a lone, rapidly spinning pulsar where a binary system once existed. This provides a potential solution to a long-standing mystery in astronomy, the origin of isolated millisecond pulsars. For years, astronomers wondered how a neutron star could be spun up to such incredible speeds without a binary partner to feed it. The Black Widow scenario provides the grim answer. The partner was there, it was just completely consumed in the process. The pulsar is left alone, a silent, spinning tombstone for the star it destroyed. This discovery profoundly impacts our understanding of how binary systems evolve and die. It reveals an incredibly violent and previously overlooked channel for stellar evolution, showing that not all binaries end in a mutual dance or a peaceful separation. Some meet a far more dramatic end. Furthermore, these systems are crucial laboratories for studying extreme physics conditions of gravity, density, and particle acceleration that we could never hope to recreate on Earth. They also have implications for the field of gravitational wave astronomy. The mergers of neutron stars are one of the universe's premier sources of gravitational waves, and understanding the population and properties of binary systems that contain them is essential for predicting what our observatories might detect. The Black Widow represents a key phase in the life story of some of these dense, exotic objects. One can't help but be struck by the profound and unsettling metaphor these systems represent. They are the universe's ultimate paradox, objects of breathtaking precision and regularity, whose very existence depends on an act of unimaginable violence and consumption. They create the most perfect natural clocks by systematically destroying their neighbors. This jarring combination of elegance and brutality forces us to expand our understanding of what is possible in the cosmos, leading us to consider objects that are not merely destructive, but whose very state of matter defies the known laws of physics. But just when you think the cosmos has shown you its most violent side, it presents a puzzle of a different kind, not one of destruction, but of bizarre and unlikely construction. We now venture from the realm of the known into the truly speculative, to a theoretical star so strange it sounds like something from the pages of a physicist's dream journal. Imagine, if you will, a star within a star, not a Russian doll, but a chimeric fusion of two of the universe's most extreme objects, a bloated, cool red giant star, millions of kilometers across and hidden deep within its fiery heart. Not a fusion core of helium, but the ultra-dense, city-sized corpse of a dead star, a neutron star. This is not a black widow consuming its partner. This is a stellar symbiote, a hybrid so profound it has earned its own name, the Thorn-Zitkow object. The very concept was born not from an observation, but from a brilliant theoretical leap. In 1977, the renowned astrophysicist Kip Thorne, famous for his work on black holes and gravitational waves, together with his then postdoctoral researcher Anna Zitkow, posed a fascinating question on paper. What would happen if a neutron star, perhaps the remnant of a supernova in a binary system, didn't get flung away but instead spiraled inward through drag and merged with its giant companion star? Their calculations suggested it wouldn't simply be destroyed. Instead, the incredibly dense neutron star could sink to the center of the red giant, displacing its core and becoming the new engine of the star. The resulting object would look like a normal, if somewhat puffy, red supergiant from the outside. But on the inside, it would be a cosmic impossibility, a stellar Frankenstein's monster powered by the intense gravitational energy of the neutron star core accreting material from the giant's enveloping gases. Dr. Emily Levesque, who has been at the forefront of the search for these objects, describes them as theoretical unicorns, whose potential discovery would fundamentally create a new classification in our stellar bestiary. The formation of such a bizarre entity is a story of cosmic violence and gravitational intimacy. It likely begins with a binary system where two massive stars are born together. The more massive of the two lives fast and dies young, exploding in a supernova and leaving behind a neutron star. If the supernova kick isn't strong enough to break the binary bond, the system remains. Over time, the companion star ages and swells into a red giant, its outer atmosphere expanding to engulf the orbiting neutron star. As the neutron star plows through this thick, gaseous envelope, it experiences drag, its orbit decaying until it finally spirals all the way down and settles into the core. There, it begins a new life, not as a dead remnant, but as the bizarre heart of a living star. The true signature of a Thorn-Zitkow object wouldn't be its size or temperature, but its unique chemical fingerprint. A normal red giant creates energy through nuclear fusion in its core, fusing hydrogen into helium and then helium into carbon and oxygen. This process leaves a specific pattern of elements on the star's surface. But the core of a Thorn-Zitkow object is different. It's a neutron star, and the nuclear reactions happen right on its surface in a process called accretion. In this incredibly hot, dense environment, a unique form of nucleosynthesis called the rapid proton capture process, or RP process, can occur. This process is thought to overproduce very specific, heavy elements like rubidium, lithium, molybdenum, and strontium, which would then be convected up to the star's surface. So, the telltale sign of one of these hybrid monsters would be a star that looks like a normal red giant, but has a bizarrely overabundant atmosphere of these particular exotic elements. For decades, the Thorn-Zitkow object remained a beautiful but unproven theory. That changed in 2014 when a team of astronomers led by Dr. Levesque announced a thrilling candidate. Using the Magellan telescopes in Chile, they were studying red supergiants in our small neighboring galaxy, the Small Magellanic Cloud. One star, named HV 2112, stood out like a sore thumb. Its spectrum showed extreme overabundances of lithium, rubidium, and molybdenum, precisely the strange cocktail predicted by Thorn and Zitkow decades earlier. The announcement sent ripples of excitement through the astrophysics community. Had we finally found one? The star was even in a binary system with a neutron star, just as the theory predicted, making it the perfect candidate. However, in science, extraordinary claims require extraordinary evidence, and skepticism is a healthy part of the process. Other researchers proposed alternative explanations. Could the strange chemistry be explained by a peculiar but otherwise normal star that had simply ingested a planet or another star rich in these elements? Could it be the result of an unusual and not yet understood phase of single-star evolution? The debate highlighted the challenges of identifying something entirely new. The initial excitement over HV 2112 has cooled somewhat, as subsequent studies have questioned the original analysis, but the search is far from over. Astronomers continue to sift through data from large sky surveys, looking for other stars with that unique elemental signature, hoping to find a more unambiguous specimen. Imagine the internal dynamics of such a star if it does exist. At its center, a neutron star, 1 billion tons compressed into a teaspoon-sized volume, spins perhaps dozens of times a second. It is constantly bombarded by a rain of gas from the inner layers of the red giant, a perpetual torrent of fuel that creates a raging inferno on its surface. This energy then slowly percolates outward through hundreds of thousands of kilometers of turbulent gas, eventually reaching the surface and making the star shine. It is a system of immense and contrasting scales, a tiny, hyperdense engine powering a vast, diffuse atmosphere. It is a star with a neutron heart, a true hybrid monster that defies simple categorization. The very existence of such an object would force us to completely rewrite our understanding of stellar evolution and the final fates of binary systems, proving once again that the universe's imagination far exceeds our own. And if a star can hide such a dense secret within its core, it makes you wonder what other extremes are possible, especially when it comes to sheer, unimaginable size. Yet if a neutron star at the heart of a red giant represents a hidden density, our next anomaly wears its immense power with brazen, terrifying brilliance. We now turn from the theoretical to the overwhelmingly empirical, to stars so colossal, so violently energetic, that their very existence was once deemed a physical impossibility. For generations, astrophysicists had calculated a firm upper limit for stellar mass, a ceiling dictated by the fundamental laws of physics. A star, they argued, could not exceed about 150 times the mass of our Sun without being torn apart by its own radiant power. It was a rule written in the equations of luminosities and forces, a boundary that the universe itself seemed to respect. That is, until we pointed our most powerful telescopes toward a frenetic stellar nursery in a neighboring galaxy and found a star that didn't just break the rule, it shattered it into 1,000,000 pieces. The discovery centered on a celestial powerhouse known as R13601, a star so monumental it redefined the very meaning of the word giant. Residing within the bustling star cluster R136, located in the heart of the magnificent Tarantula Nebula in the Large Magellanic Cloud, this stellar behemoth was first studied in detail using the European Southern Observatory's Very Large Telescope. The data was nothing short of staggering. Initial estimates suggested a mass of 265 solar masses, and while later, more refined observations have brought that number down slightly, it still confidently sits at over 250 times the mass of our Sun. To put that in perspective, if you placed R13601 at the center of our solar system, its outer atmosphere would extend well beyond the orbit of Mercury, and its sheer brightness would be almost unimaginable. It shines with the luminosity of nearly 9 million suns. Its surface temperature is a blistering 53,000 degrees Celsius, over 9 times hotter than our own star. This wasn't just a star, it was a cosmic titan, a challenge to every textbook chapter on stellar structure. The implications of such a monstrous star are as profound as they are violent. These supermassive stars live by a brutal philosophy: live fast, die young, and leave a spectacular corpse. A star like R13601 burns through its nuclear fuel at a ferocious, profligate rate. Despite its immense reservoir of hydrogen, its staggering luminosity means it can only sustain itself for a brief cosmic moment, perhaps only 2 or 3 million years. In comparison, our Sun will shine steadily for over 10 billion years. This short, brilliant life is not a quiet one. These stars dominate their surroundings, flooding their galactic neighborhood with enormous amounts of ultraviolet ionizing radiation and powerful stellar winds. These winds, flowing from the star's surface at millions of kilometers per hour, act like cosmic sandblasters, shaping nearby gas clouds, preventing star formation in some areas and potentially triggering it in others. They are the ultimate influencers of their galactic environment, their brief lives dictating the fates of countless other stars around them. But how does a star grow to such an impossible size? How does it avoid the so-called Eddington limit, the point where the outward pressure of its own radiation becomes so intense that it overcomes gravity and begins to blow the star apart? This is the central puzzle that theorists have been grappling with. One compelling explanation points to the chaotic environment of a dense star cluster, like the home of R13601. In such a crowded nursery, young stars are born in close proximity. It's possible that these stellar titans are not born as single entities, but are the product of dramatic stellar mergers, where two or more large stars collide and coalesce into a single, more massive object early in their lives. Other mechanisms, like rapid accretion from the dense surrounding gas cloud, could also play a role. Furthermore, the star's own rotation or incredibly strong magnetic fields might provide the necessary stability. These factors could help channel the star's intense radiation, allowing it to hold itself together in a precarious balance, like a spinning top that stays upright only through its rapid motion. It's a fragile existence, forever on the verge of flying apart, yet it persists through its own incredible dynamism. The death of such a star is as extraordinary as its life. It does not go gentle into that good night. Current models suggest that when a star of this mass finally exhausts its fuel, its core may become so hot that it begins to produce matter and antimatter electron and positron pairs. This process saps the core's energy pressure, leading to a catastrophic collapse that triggers a runaway thermonuclear explosion. The result is a pair instability supernova, an event so utterly violent and energetic that it can briefly outshine an entire galaxy. In the most extreme cases, the explosion is so complete that it leaves behind no black hole or neutron star. The entire star is completely annihilated, scattering its enriched guts across space. The elements forged in its core and during its spectacular death, including heavy elements like gold and uranium, are flung into the cosmos, eventually becoming part of new stars, new planets, and perhaps new life. The existence of these supermassive stars forces us to reconsider the entire life cycle of matter in the universe. The Tarantula Nebula serves as a perfect cosmic laboratory for studying these giants. This vast, roiling cloud of gas and dust is the most active star-forming region in our galactic neighborhood, a place where the processes of stellar birth and death are playing out on an epic scale. Here, astronomers have identified dozens of stars exceeding 100 solar masses, with R13601 being the most extreme confirmed example. Studying this population is crucial because it tells us that R13601 is not a singular freak of nature, but rather the most spectacular member of a previously overlooked class of celestial object. This realization opens up a universe of questions. How many of these titans are lurking undetected in other intense starburst regions? Did the early universe, which was richer in the pristine gas needed for star formation, produce even larger stars that have long since died? Every new observation pushes the boundaries of what we thought was possible, revealing a cosmos that is far more dynamic and extreme than we ever imagined. This journey into the realm of the impossibly massive naturally makes one wonder about the opposite extreme, not stars that defy size limits, but those that seemingly defy the most fundamental limit of all, time itself. Just when we think we've grasped the scale of cosmic time, the universe presents us with a paradox so profound it seems to defy logic itself. We've marveled at stars that die and come back, stars that flee their galaxies, and stars of impossible size. But now we encounter a challenge to our most fundamental timeline, a star that appears to be older than the universe it inhabits. This isn't a theoretical puzzle. It's a direct, observational conundrum that strikes at the very heart of cosmology and forces us to question the precision of our cosmic clocks. The star at the center of this mystery is known as HD 140283, but it has earned a far more dramatic nickname, the Methuselah star. Located a mere 190 light-years away in the constellation of Libra, this unassuming dot of light became a global sensation when detailed studies revealed its estimated age was approximately 14.5 billion years. This number sent shockwaves through the scientific community because the most precise measurements of the universe's age derived from the cosmic microwave background radiation by observatories like the Planck satellite peg it at 13.8 billion years. The implication was as startling as it was simple. How can a star be older than the space that contains it? It would be like finding a coin minted in 1920, tucked inside a treasure chest sealed in 1890. The discovery didn't just break a rule. It suggested our entire historical narrative might be missing a few crucial chapters. Determining the age of a single star is one of the most complex and delicate tasks in all of astronomy. It's not like counting tree rings. There's no direct method. Instead, astrophysicists rely on a sophisticated combination of observations and stellar evolution models. For a star like HD 140283, which is a metal-poor subgiant, meaning it has low abundance of elements heavier than helium and is in a transitional phase of its life, the process is particularly nuanced. Astronomers use incredibly precise parallax measurements from missions like Gaia to pin down its distance with extraordinary accuracy. Once they know its distance, they can calculate its intrinsic brightness or absolute magnitude. They then take detailed spectroscopic readings to determine its surface temperature, gravitational force, and most critically, its chemical composition, specifically the ratios of key elements like oxygen, iron, and helium. This collection of data points luminosity, temperature, mass, and composition is then compared against sophisticated computer models that simulate the life cycles of stars. The goal is to find the model track for a star with those exact properties that ends up precisely at the point where HD 140283 is now in its evolution. The length of time that model star took to reach that point is the estimated age. It's a brilliant piece of cosmic detective work, but it is filled with potential pitfalls. The immense uncertainty in this process is where the solution to the Methuselah paradox likely lies. The initial estimate of 14.5 billion years was not a fixed number, but the center of a range with significant error bars. Astronomers like Howard Bond of the Space Telescope Science Institute have dedicated years to refining this measurement. The largest source of uncertainty revolves around the star's oxygen abundance. Oxygen plays a crucial role in the opacity of a star's interior. More oxygen makes the star more opaque, which changes how energy is transported from the core to the surface. A more opaque star burns its fuel more slowly, making it appear older for a given set of properties. Early measurements had a relatively high uncertainty in the oxygen content. When subsequent, more precise spectroscopic observations indicated the star had a higher oxygen abundance than initially thought, the models were adjusted. This single revision brought the star's estimated age down significantly. Furthermore, the amount of helium diffused downward in the star's layers over its lifetime also affects the models. Every slight adjustment to these input parameters tweaks the final age estimate. The Hubble Space Telescope played a pivotal role in this cosmic age arbitration. By refining the star's distance measurement to an accuracy of just over 0.5%, Hubble's data allowed for a much more precise calculation of its intrinsic brightness. This tighter constraint was a key factor that allowed Howard Bond and his team to announce a revised age estimate in 2013 of 14.46 billion years, but now with an uncertainty of plus or minus 800 million years. This was a monumental step. That margin of error now officially overlaps with the age of the universe. In other words, the star's age is entirely consistent with the cosmos, sitting right on the borderline. The paradox from a purely statistical standpoint was resolved, yet the central intrigue remains. The best estimate still points to an age that is tantalizingly, provocatively old, a whisper from a time before time as we define it. The media frenzy around HD 140283 was a fascinating episode in how science interacts with the public. Headlines proclaiming "star older than the universe" were catnip for readers, suggesting a fundamental crack in the foundation of modern physics. For scientists, however, it was never about overturning the Big Bang Theory. It was a powerful stress test. It highlighted the exquisite precision of our models and revealed the subtle, hidden dependencies within them. It forced astrophysicists to scrutinize every assumption, every variable, and every line of code in their stellar evolution simulations. This process of being challenged by observation is how science strengthens itself. The Methuselah star didn't break cosmology, it made it more robust. Ultimately, the lesson of this ancient sun is one of beautiful humility. It reminds us that our measurements of the cosmos are not absolute truths etched in stone, but the current best approximations based on an ever-growing body of knowledge. It invites us to consider the possibility that our understanding of the universe's first moments is still incomplete, or that the physics governing the earliest stars might have nuances we have yet to incorporate. The star's silent, ancient light continues to beam its puzzle toward us, not as a threat to our understanding, but as an invitation to look deeper, measure more precisely, and think more creatively. And as we ponder the limits of what can be known about the oldest stars, our curiosity is naturally drawn to the opposite end of the spectrum, to objects so faint and cool they barely qualify as stars at all, hiding in the dark spaces between the brilliant points of light. But what if the first stars to ever shine in the cosmos weren't stars as we know them at all? What if, before the first flicker of nuclear fusion ever ignited, the universe was illuminated by something far more strange and spectacular, giants powered not by ordinary matter, but by the invisible, mysterious substance that makes up most of the mass in the universe? We are venturing now into the realm of the purely theoretical, to a concept that sounds like it belongs in the realm of fantasy, the dark star. These hypothetical behemoths are thought to be colossal structures, vast spheres of primordial hydrogen and helium that could have been larger than our entire solar system, yet they would have glowed with a warm, steady light, sustained not by the fire of nuclear reactions, but by the annihilation of dark matter particles at their cores. The very idea of a dark star forces us to reimagine the cosmic dawn, that period a few 100 million years after the Big Bang when the first structures began to coalesce out of the expanding darkness. In the Standard Model, the first stars, known as Population 3 stars, were immense, short-lived giants that lit up through nuclear fusion and quickly exploded, seeding the universe with the first heavy elements. But a team of theorists, including Catherine Fries, Paolo Gondolo, and Douglas Spoliar, proposed a captivating alternative. They wondered, what if the dense clouds of gas that were collapsing to form these first stars were also incredibly rich in dark matter? In the early universe, dark matter was much more densely packed and could have been pulled into the gravitational well of these nascent stellar objects. If a certain type of dark matter particle exists, one that is its own antiparticle, then these particles would annihilate upon contact with each other, releasing a tremendous amount of energy in the form of heat and light. This energy, the theorists argued, could have been enough to halt the gravitational collapse of the gas cloud, preventing it from ever becoming dense and hot enough to ignite nuclear fusion. Instead, it would have stabilized as a vast, puffy ball of gas, heated from within by this exotic dark matter engine. The physics behind this process is both elegant and profoundly strange. The dark matter particles, gravitationally trapped at the center of the gas cloud, would continuously annihilate. This annihilation produces a steady and intense outpouring of energy. This energy, radiating outward, creates an outward pressure that counteracts the inward pull of gravity. It's a perfect, stable equilibrium. As the gas cloud tries to contract and heat up, the annihilation rate increases, pumping out more energy and pushing back against the collapse. The result is a star that can exist for millions of years in this suspended state, a glowing orb whose power source is fundamentally different from any star we have ever observed. The properties of such an object are almost mind-bending. A dark star would be enormous, with a diameter that could easily span the distance from the Sun to Pluto and beyond. Yet, despite its incredible size, its surface temperature would be relatively low, perhaps similar to our Sun's, meaning it would glow with a familiar yellowish-white light. It would be a diffuse giant, a cosmic will-o'-the-wisp of unimaginable scale. The potential role of these dark stars in shaping the early universe is immense. Their longevity and incredible size could provide a compelling explanation for one of the most persistent puzzles in modern cosmology, the rapid formation of supermassive black holes. We now know that supermassive black holes, weighing billions of times the mass of our Sun, existed when the universe was less than 1 billion years old. It's incredibly difficult for standard models to explain how such monsters grew so big so fast, but a dark star offers a perfect seed. After millions of years, the dark matter fuel at its core might eventually be depleted. Once the annihilation energy wanes, the gigantic, unstable ball of gas would be free to collapse under its own immense weight. Because it started out so enormous, this direct collapse could form a black hole with a mass thousands of times that of our Sun right from the very beginning. This massive seed black hole would then have a tremendous head start on accreting more material, quickly growing into the supermassive behemoths we see at the hearts of early galaxies. Furthermore, the intense, steady ultraviolet radiation from a population of dark stars could have played a significant role in the reionization of the universe, stripping electrons from the neutral hydrogen atoms that filled space and making the universe transparent to light for the first time. The most thrilling aspect of this theory is that it might be testable. The James Webb Space Telescope, with its unprecedented ability to peer back to the very first galaxies, could be the instrument that finds evidence for these dark giants. Theorists suggest that if dark stars ever existed, they would be incredibly bright in the infrared part of the spectrum due to their vast size and relatively cool surfaces. JWST might be able to detect them as point-like sources of infrared light that are far too red and luminous to be explained by any known type of star or galaxy. They would appear as singular, mysterious anomalies in the deep field images, objects that defy classification under our current understanding of stellar physics. The hunt is already on, with astronomers meticulously scanning JWST data for any candidate that matches this unique signature. Finding one would be a discovery of Nobel Prize-winning magnitude, providing not just evidence for a new type of star, but our first direct glimpse into the properties and behavior of dark matter itself. Pondering the existence of dark stars forces us to confront the deepest questions about the nature of the universe's most abundant yet most elusive component. Is dark matter made of particles that can annihilate? Did the architecture of the first stars depend on a delicate dance between visible and invisible matter? The concept of a dark star is a beautiful reminder that our universe might harbor phenomena that are beyond our current imagination, waiting for the right telescope, the right theory, or the right moment to be revealed. It represents the cutting edge of theoretical astrophysics, where bold ideas reach across the void to explain the unknown. And while we search the ancient light for signs of these dark giants, we are simultaneously discovering stars at the opposite end of the spectrum, not immense and theoretical, but small, cold, and very, very real, challenging our definitions in an entirely different way. After contemplating stars powered by the invisible hand of dark matter, we now turn our attention to a class of objects that are very much real, yet so astonishingly cold they defy the very term star as we know it. Imagine a celestial body that forms like a star from a collapsing cloud of gas and dust, but never achieves the glorious nuclear fire that defines a true sun. Instead, it simply cools, fading from a warm glow to a temperature you might find on a pleasant afternoon on Earth. These are not stars in the traditional sense, nor are they planets. They are the enigmatic white dwarfs, the coldest known members of the brown dwarf family, and they exist in a strange, twilight zone that is forcing astronomers to rewrite the definitions in their textbooks. The discovery of these cosmic coolants is a testament to our technological ingenuity, as they are utterly invisible to telescopes searching invisible light. Their detection hinges entirely on their faint warmth, a subtle heat signature that can only be picked up by powerful infrared observatories. Missions like NASA's Wide Field Infrared Survey Explorer, or WISE, and the Spitzer Space Telescope have been instrumental in this hunt, scanning the skies for points of light that are unusually red and incredibly dim. Dr. Michael Cushing, a leading astronomer in the study of brown dwarfs, often describes this process as looking for a cosmic needle in a haystack, where the needle is only glowing with the heat of a smoldering ember. The key to identifying a white dwarf lies in its spectrum, the unique fingerprint of light that reveals its composition and temperature. In these frigid objects, the telltale signs are deep absorption bands from molecules like methane, and in the very coldest ones, even water vapor condensing into clouds within their atmospheres. It's a spectrum that looks far more like that of a giant planet like Jupiter than any star we're familiar with. So what keeps these failed stars warm if not fusion? The answer lies in their birth. When a brown dwarf first condenses, it generates a tremendous amount of heat through the simple, relentless process of gravitational contraction. As the cloud pulls itself together under its own weight, the potential energy of that collapse is converted into thermal energy, heating the nascent object. For a brief time, the very largest brown dwarfs might even trigger fleeting deuterium fusion, a heavier isotope of hydrogen in their cores, but this fuel is quickly exhausted. After that, there is no new source of heat. The brown dwarf simply radiates its initial store of thermal energy out into space, cooling down inexorably over billions of years, destined to end its life as a cold, dark, almost planet-like cinder. A white dwarf represents the final, coldest stage of this long cooling process, a fading ember from a fire that never truly caught. To truly appreciate the bizarre nature of these objects, we need only look at a specific example, one that holds the record as one of the coldest known bodies of its kind, WISE 0855-0714. Located just 7.2 light-years away, It is one of our closest neighbors, yet it is so frigid and faint that it was only discovered in 2014. Follow-up studies revealed its surface temperature to be between -48 and -13 degrees Fahrenheit, which is right around -25 to -25 degrees Celsius colder than a winter day in Siberia. Intriguingly, detailed infrared spectroscopy has provided strong evidence that this lonely wanderer has a cloudy atmosphere, likely filled with water ice or sulfide clouds, not unlike the weather patterns on a gas giant planet. It is a stunning realization. We are studying the meteorology of an object that formed as a star, a world that is essentially a floating, Jupiter-like planet with no sun of its own to orbit. This discovery forces a profound re-examination of the line we draw between a star and a planet. The classical definition of a star is an object massive enough to sustain core hydrogen fusion. A planet forms from the leftover material in a disk around a star, but a brown dwarf, and particularly a white dwarf, blurs this distinction entirely. It forms like a star directly from a collapsing cloud, yet it never achieves fusion and ends up with a temperature, atmosphere, and appearance startlingly similar to a planet. This has led to spirited debates among astronomers. Should we classify the very largest planets as failed stars, or should we think of the smallest brown dwarfs as rogue planets that formed on their own? The existence of white dwarfs shows us that nature doesn't care for our neat categories. It produces a continuous spectrum of objects, from the brightest suns to the darkest, coldest orbs, and it is up to us to make sense of it all. One can't help but engage in a captivating thought experiment. Imagine standing on a planet orbiting a star like our Sun, but in a system that also has a white dwarf drifting in its outer reaches. To the naked eye, this cold neighbor would be completely invisible, a dark ghost in the system. But with infrared sensors, you could watch it, a faint, deep crimson disk hanging in the blackness, its cloud pattern slowly shifting over centuries, a permanent testament to the quiet, cold majority of objects that populate our galaxy. It is a humbling reminder that for every brilliant, fusion-powered star like our Sun, there are likely countless more of these dark, cool failures silently wandering the interstellar void. This journey to the absolute lower limit of stellar temperature prepares us for a dramatic shift in perspective towards objects that represent the upper extreme of magnetic ferocity in the universe. Yet if the cold, quiet fade of a white dwarf represents one end of stellar existence, our next anomaly catapults us to the polar opposite, a realm of such unimaginable, violent energy that it defies all earthly comparison. We now venture into the domain of the Magnetar, a celestial object so ferociously magnetic that its very presence in the cosmos redefines the word extreme. To grasp its power, consider this. The Earth's magnetic field is strong enough to gently guide a compass needle. A typical refrigerator magnet has a field of about 100 Gauss. The most powerful magnets we can create in laboratories might reach 1,000,000 Gauss, but a magnetar boasts a magnetic field of a quadrillion Gauss. That is a 1 followed by 15 zeros. This isn't just a stronger magnet. This is a fundamental force of nature so potent it warps the very fabric of reality around it. The effects of such a field on matter are not just dramatic, they are utterly surreal. Within the sphere of a magnetar's influence, the structure of atoms themselves is torn apart. The magnetic field is so powerful that it distorts the electron clouds surrounding atoms into long, thin cylinders, effectively turning matter into a strange, one-dimensional plasma. If a human were to venture within a few thousand kilometers of a magnetar, a purely theoretical and fatal scenario, the magnetic field would literally rip you apart at the atomic level, pulling the iron from your blood and polarizing your molecules before you even knew what was happening. But the violence isn't just reserved for hypothetical visitors. The magnetar itself is a victim of its own power. The crust of the neutron star, a crystalline lattice of incredibly dense iron nuclei, is under immense strain from these magnetic forces. Periodically, this crust will fracture and shift in a cataclysm known as a starquake, an event that releases more energy in a fraction of a second than our Sun will emit in 100,000 years. This pent-up energy isn't just released as a simple crack. It is ejected in the most spectacularly violent outbursts in the present-day universe, giant flares. On December 27, 2004, a blast of gamma rays and X-rays swept through our solar system, originating from a magnetar known as SGR 1806-20, located 50,000 light-years away on the far side of our galaxy. For 0.2 of a second, this flare released more energy than our Sun has emitted in the last 250,000 years. The wave of radiation was so powerful that it actually compressed Earth's magnetic field and significantly ionized our upper atmosphere, disrupting long-range radio communications. If this event had occurred within 10 light-years of Earth, it is believed it could have triggered a mass extinction by stripping away our protective ozone layer. Thankfully, the closest known magnetar is still much farther away, but the event served as a stark reminder that we live in a galaxy where distant, exotic objects can reach out and touch us across unimaginable voids. So how does nature forge such a monstrous object? Magnetars are born in the most violent deaths imaginable, the supernova explosions of massive, rapidly spinning stars. Astronomers believe the progenitor star must have itself possessed an unusually strong magnetic field. As the star's core collapses into a neutron star, the conservation of magnetic flux, a fundamental principle of electromagnetism, causes that field to be amplified exponentially. Imagine taking the magnetic field of a large star and compressing it down into an object only 20 kilometers across. This process, combined with a theorized dynamo effect driven by the incredible heat and turbulent fluid motions in the newborn neutron star's first few seconds, can turbocharge the magnetic field to magnetar levels. It's a perfect storm of stellar physics, a massive magnetic star that spins rapidly as it dies, creating a neutron star with a wound-up magnetic spring that is tighter and more tense than any other object in the cosmos. The life of a magnetar is a story of gradual, magnificent decay. Unlike pulsars, which are powered by their rapid rotation, the intense activity of a magnetar is fueled by the slow, agonizing decay of its unimaginable magnetic field. This decaying field pumps energy into the neutron star's crust, heating it, stressing it, and ultimately powering the spectacular X-ray and gamma-ray flares that define these objects. Over tens of thousands of years, as the magnetic field slowly dissipates its energy, the magnetar will quiet down, eventually becoming a more ordinary, though still incredibly dense, neutron star. Their hyperactivity is a phase, a tumultuous adolescence in the life of a dead star, but it is a phase that makes them some of the most dynamic and dangerous objects we have ever identified. In recent years, the mystery of magnetars has deepened in the most thrilling way, linking them to one of astronomy's most perplexing new phenomena, fast radio bursts. These are incredibly brief, intensely bright flashes of radio waves that come from distant galaxies, lasting only milliseconds yet emitting as much energy as the Sun does in days. For years, their origin was a complete enigma, with theories ranging from merging black holes to alien spacecraft. Then, in April 2020, a magnetar within our own galaxy, SGR 1935+2154, emitted a radio burst that was, for a fleeting moment, as bright as some of the extragalactic fast radio bursts. This was the smoking gun. While not all fast radio bursts may come from magnetars, this event proved that these magnetic monsters are capable of producing them, likely through their immense starquakes or sudden magnetic reconnection events. It was a monumental connection tying together two of the most extreme puzzles in modern astrophysics. One is left to ponder the sheer, raw power contained within such an object. What could humanity ever hope to do with such energy? Could we even comprehend it? The magnetic field of a magnetar is so strong that if one were located at the distance of our moon, it would erase the magnetic strips on every credit card on Earth. It is a force that renders our greatest technological achievements utterly insignificant. Yet, by studying these terrifying behemoths, we are learning about the behavior of matter under conditions so extreme they can never be replicated on Earth, probing the very laws of physics itself. They are natural laboratories for the most fundamental science, teaching us about the limits of magnetic fields, the nature of dense matter, and the wild, untamed physics that governs the universe's most exotic corners. This exploration of ultimate magnetic power naturally makes us wonder about other forms of stellar defiance, particularly stars that seem to possess a secret to eternal youth. After witnessing the terrifying magnetic fury of magnetars, we now turn to a stellar anomaly that is less about raw power and more about a profound cosmic paradox, stars that seem to have discovered a secret fountain of youth. In the serene, ancient cities of stars known as globular clusters, where suns are typically old, red, and cooling, astronomers keep finding defiant rebels that simply refuse to grow old. These are the blue stragglers, stars that shine with a brilliant, hot blue light, standing out starkly against the faded crimson backdrop of their elderly neighbors. Their very existence is a direct challenge to our understanding of stellar life cycles, presenting a beautiful mystery. How can a star appear younger than the cluster it was born with? The story of their discovery begins in the early 1950s with the pioneering astronomer Alan Sandage. While studying the color magnitude diagrams of globular clusters, a kind of census that plots stars by their brightness and color, he noticed something that shouldn't be there. These diagrams act as a stellar family portrait, showing how a population of stars born at the same time has aged. In every old cluster, the vast majority of stars had already left the main sequence, evolving into the red giant phase as expected. But there was a stubborn group of stars that lingered on the main sequence, burning hot and blue long after their siblings had cooled and reddened. They were straggling behind in their evolution, and their blue color made them impossible to ignore. Their presence was initially so baffling that some astronomers wondered if they might be interlopers, younger stars that had somehow wandered into the ancient cluster. But the physics of globular clusters made that impossible. Their immense gravitational pull would prevent any such youthful intruder from entering. The blue stragglers were bona fide members, and their youthful vigor was a genuine, homegrown puzzle. The significance of this discovery cannot be overstated. In stellar astrophysics, mass is destiny. A star's mass determines how quickly it burns through its nuclear fuel and how it evolves. In a cluster where all stars were born simultaneously over 10 billion years ago, every star above a certain mass should have exhausted its hydrogen fuel long ago and moved off the main sequence. The fact that these massive, blue, and therefore fuel-hungry stars are still shining means that somehow, against all odds, they have acquired a new lease on life. They have found a way to top up their fuel tanks or restart their engines, effectively resetting their evolutionary clocks. As Dr. Francesca D'Antona, an astrophysicist who has modeled these stars, explains, they are stellar vampires. They refuse to follow the rules of aging by taking mass from a companion. This vivid metaphor points us directly toward the two leading theories that explain their rebellious nature. The first and most widely accepted mechanism is a cosmic heist through mass transfer in a binary system. Imagine two stars born as a close-knit binary pair. As the more massive star ages, it swells into a red giant. If the stars are close enough, the gravitational pull of the smaller companion can strip away the outer layers of the giant, siphoning hydrogen-rich material onto itself. This incoming fuel rejuvenates the recipient star, providing it with a fresh supply of hydrogen to burn and making it hotter, bluer, and more massive than it was originally. It's a stellar facelift paid for by a celestial donor. The second theory involves a far more dramatic and violent encounter, a direct collision, in the incredibly dense cores of globular clusters, where stars can be packed thousands of times more tightly than in our neighborhood. Stellar traffic accidents are not just possible, they are inevitable. When two lower mass stars collide and merge, they can create a single, new, more massive star. This newly formed star has a larger reservoir of hydrogen and, having just been born from the merger, appears younger and bluer than its contemporaries. It's a stellar phoenix, not rising from ashes, but from the merger of its predecessors. Observational evidence has steadily accumulated to support both of these thrilling scenarios. The Hubble Space Telescope has been instrumental in this detective work, its sharp vision allowing astronomers to resolve individual stars in distant clusters. In many cases, careful monitoring has revealed that blue stragglers are indeed often part of binary systems, their subtle rhythmic wobbles betraying the presence of a companion. In other cases, studies of their rotation rates provide clues. Stars that have gained mass through accretion often spin at incredibly high velocities, a telltale sign of the angular momentum transferred during the process. The cluster M30 serves as a perfect celestial laboratory. It contains a rich population of blue stragglers, and their distribution is highly revealing. They are overwhelmingly concentrated in the cluster's densely packed core, exactly where both binary interactions and direct collisions would be most frequent. This spatial correlation is a powerful piece of evidence that their formation is intrinsically linked to the social dynamics of a crowded stellar environment. There's a fascinating anecdote from the study of another cluster, M67, that highlights the subtlety of this work. Astronomers found a blue straggler that was pulsating, rhythmically varying in brightness. This pulsation allowed them to peer into its interior using astroseismology, much like geologists use earthquakes to study Earth's core. The data suggested this star had a core that was older and more evolved than its hot, blue exterior would suggest, a clear signature of a star that had been rejuvenated from the outside, perfectly matching the mass transfer theory. It was a star wearing a youthful mask over an old soul. This concept of stellar vampirism is a metaphor that resonates deeply. It paints a picture of the cosmos not as a placid and peaceful void, but as a dynamic arena where stars interact, compete, and even steal from one another to survive. The blue straggler, shining with stolen vigor, is a testament to the fact that evolution in a dense cluster is a contact sport. Their existence teaches us that a star's life story is not always a solitary journey. It can be dramatically altered by its relationships with its neighbors. This understanding helps astrophysicists model the complex dynamical processes, the gravitational dances, the close encounters, the mergers, that shape the long-term evolution of these ancient stellar cities. By studying these rebellious stars, we are essentially reading the history of their cluster's social interactions written in their light. This journey from a star that steals mass to stay young, naturally, guides our curiosity toward stars that have undergone a far more extreme transformation, not gaining a new atmosphere but revealing a startlingly bare and dense core. After exploring stars that steal mass to stay forever young, we now descend into the final, eerie aftermath of stellar death, where the universe reveals yet another layer of its strangeness. Imagine the corpse of a star, a white dwarf, an Earth-sized diamond of degenerate matter, slowly cooling into oblivion over billions of years. For over a century, our models of these stellar remnants were clear and elegant. Their atmospheres, we believed, would be pristine and simple, dominated by either the lightest element, hydrogen, or the second lightest, helium, which should float to the surface as the star cools. It was a tidy, predictable end to a star's life, but the cosmos, it seems, has a deep aversion to tidiness. Astronomers, while conducting vast spectral surveys of the sky, began to find white dwarfs that defied this peaceful retirement. These weren't covered in hydrogen or helium. Their surfaces, their very atmospheres, were shockingly dominated by oxygen, an element so heavy it should have sunk into the star's depths long ago, never to be seen again. The discovery of these oxygen-rich white dwarfs was not a single eureka moment, but a gradual dawning of disbelief as data from the Sloan Digital Sky Survey piled up. Researchers sifting through the spectra of thousands of white dwarfs kept finding a handful with bizarre, unrecognizable signatures. The familiar fingerprints of hydrogen and helium were absent. Instead, the light was being absorbed by something else entirely. When they finally decoded the message, the result was staggering. The atmosphere was almost pure oxygen. This was akin to finding a pristine, ancient iceberg not made of water ice but solid, frozen oxygen. It made no sense according to the standard playbook of stellar evolution. As Dr. Boris Genzik, an astrophysicist who studies these exotic remnants, put it, this was a complete surprise. We have a number of mechanisms that explain why we see hydrogen or helium on the surface of white dwarfs, but no simple, obvious reason for oxygen. It forces us to reconsider our models of how stars die and what happens in their final moments. The implications of this discovery are profound, pointing toward a dramatically different and far more violent death for the stars that spawned these oddities. A typical white dwarf is the exposed core of a low to medium mass star, left behind after it gently puffs off its outer layers to form a planetary nebula. That core is primarily carbon and oxygen, the ashes of helium fusion, blanketed by thin layers of helium and hydrogen. But these oxygen-rich white dwarfs suggest their progenitor stars experienced something far more catastrophic. The leading theory is a phenomenon known as an off-center ignition. In a massive star just below the threshold for a core collapse supernova, helium fusion might not ignite in the very center of the core. Instead, it could ignite in a shell around the center. This creates a ferocious convective flame that burns outward, violently disrupting the star's structure. This process could strip away all the lighter outer layers, the hydrogen and helium, before the star even has a chance to eject them peacefully, leaving behind a bare, exposed core of oxygen and neon for all the universe to see. It's a stellar death that is more akin to a violent unveiling than a quiet fading. But how does this oxygen atmosphere actually persist? Why doesn't the oxygen itself sink under its own weight, drawn by the white dwarf's immense surface gravity? This is where the mystery deepens into a fascinating puzzle of stellar forensics. The current hypothesis involves a delicate and temporary balance of forces. White dwarfs are so dense that gravity should quickly separate their elements, with the heaviest sinking to the bottom. For an oxygen atmosphere to exist, something must be actively holding it up at the surface. One compelling idea is that the white dwarf's own residual heat is creating a shallow convection zone, a thin layer of bubbling plasma that is churning just enough to keep the oxygen atoms buoyant and prevent them from sinking. It's a bit like a pot of water that is kept just at a simmer with tiny bubbles preventing heavier particles from settling to the bottom. However, this is a transient state. As the white dwarf continues to cool over millions of years, this convection will eventually cease, and the oxygen will finally sink, perhaps leaving behind a more conventional helium-dominated surface. We may be catching these extraordinary objects in a very brief and very strange phase of their cosmic retirement. To understand this anomaly, we must look at a specific celestial specimen, a star that has become the poster child for this entire bizarre class, SDSS J124043.01 plus 67103.4.68. This mouthful of a name belongs to a white dwarf located about 1,100 light-years from Earth, and it is the most extreme example we have. Detailed spectroscopic analysis has revealed its atmosphere to be 99.9% pure oxygen, with only trace amounts of other elements like neon and magnesium. It is, for all intents and purposes, an oxygen world. The existence of such a pure object is what forced astronomers to rule out simpler explanations, like surface pollution from accreted planetary debris. A devoured asteroid or planet would have left a much more mixed and messy chemical signature. The purity of the oxygen here points to an intrinsic origin, a story written in the star's own fiery death throes. This particular white dwarf is a clean laboratory, offering a direct view into the products of nuclear fusion that occurred deep within the star long ago. The case of SDSS J124043 doesn't just present a curiosity, it actively challenges our fundamental models of stellar interiors and nucleosynthesis. The very fact that we can see an oxygen-dominated surface means that our understanding of how elements are layered inside a dying star and how those layers are revealed is incomplete. It suggests that the final stages of nuclear burning can be far more turbulent and asymmetrical than our one-dimensional models assume. Furthermore, the specific ratios of oxygen to other elements like neon and magnesium on the surface provide critical clues. These ratios are the direct output of specific nuclear reactions, and by measuring them, astronomers can work backwards to determine the precise temperature, density, and conditions inside the star during its final, violent phases. This white dwarf is therefore not just a dead star, it is a cosmic Rosetta Stone helping us decode the language of stellar death. This discovery inevitably sparks a larger, more tantalizing question. If white dwarfs can have oxygen atmospheres, what other exotic surfaces might be out there? Could there be white dwarfs with carbon-dominated atmospheres, the bare cores of stars that never managed to fuse carbon into heavier elements? What about neon-rich surfaces or even more exotic chemistries? The hunt is now on, with astronomers re-examining spectral surveys with fresh eyes, looking for other anomalies that were previously dismissed as noise or error. Each new find has the potential to reveal a new and unexpected pathway in stellar evolution, showing us that the death of a star is not a single, predictable event, but a diverse family of outcomes with its own rare and bizarre branches. This foray into the strange chemistry of stellar corpses prepares us for a different kind of mystery, one not of composition, but of rhythm, a star that doesn't just shine with an unusual light, but beats with a puzzling and irregular pulse. But just as we begin to unravel the secrets of one type of pulsating star, the cosmos reveals another layer of mystery, proving that even the most reliable clocks can sometimes develop a perplexing stutter. For over a century, astronomers have relied on the steady, rhythmic beating of Era Lyrae stars as one of the most trusted tools for measuring vast distances across our galaxy. These variable stars pulse with a predictable regularity, expanding and contracting in a cycle that typically lasts less than a day, their brightness rising and falling with a metronome-like consistency that makes them perfect standard candles. They are the cosmic lighthouses of the Milky Way, their intrinsic brightness known so well that we can calculate how far away they are simply by observing how dim they appear to us. It is a foundational pillar of the cosmic distance ladder. That is, until we discovered that some of these lighthouses have a flicker, a strange, unpredictable wobble in their pulse that defies all simple explanation. This enigma is known as the Blasco effect, and it has been confounding astrophysicists since it was first described by Russian astronomer Sergei Blasco way back in 1907. Imagine listening to a perfectly tuned grandfather clock, its pendulum swinging with a dependable tick-tock week after week. Then, one day, you notice the ticks are suddenly quieter, and the time between them has imperceptibly lengthened. A month later, the volume and rhythm have returned to normal, only to change again a few weeks after that. This is the essence of the Blasco effect. In a star that should be the picture of regularity, astronomers observe a long-term modulation, a secondary cycle that can last anywhere from 20 to 200 days. During this cycle, the amplitude of the pulsation, the difference between its brightest and dimmest point, changes dramatically. Even more puzzling, the period of the pulsation itself, the very heartbeat of the star, can speed up or slow down slightly. It's as if the star's entire internal engine is breathing in and out over a much longer timescale, affecting its most fundamental rhythm. Dr. Katrian Kohlenberg, a leading researcher on the phenomenon, has called it one of the longest-standing unsolved problems in stellar astrophysics, a testament to how a century of study has yet to yield a definitive answer. The importance of solving this puzzle extends far beyond mere academic curiosity. The entire utility of Era Lyrae stars as standard candles hinges on their predictability. The Blasco effect introduces a troublesome uncertainty into our distance measurements. If we cannot be absolutely sure of a star's true intrinsic brightness at any given moment because it is in the midst of one of these mysterious modulations, then our calculation of its distance becomes less precise. On the grand scale of mapping the Milky Way, these small errors can accumulate, potentially blurring our three-dimensional picture of our own galactic neighborhood. More profoundly, the effect is believed to be a crucial clue, a visible symptom of the incredibly complex physics occurring deep within the star's interior. Understanding it would give us an unprecedented window into the processes that govern stellar structure, convection, and energy transport in these aging suns. It is a direct probe into the hidden dynamics of a star's heart. So what causes this strange behavior? Theorists have proposed a captivating array of possibilities, each more complex than the last. One prominent idea involves a magnetic cycle, analogous to the 11-year sunspot cycle on our sun, but on a much more intense and compressed scale. The theory suggests that a periodically strengthening and weakening magnetic field deep within the star could be altering how energy is transported from the core, thereby affecting the pulsation mechanism. Another compelling hypothesis points to resonance, where two different pulsation modes inside the star interact and interfere with each other. Think of it like two different musical notes being played simultaneously, creating a pulsating beat frequency. The Blasco effect would be that audible beat. Yet another theory invokes the influence of a binary companion star, whose gravitational tug as it orbits could periodically perturb the Era Lyrae star's outer layers, enough to influence its pulsation characteristics. However, exhaustive searches have failed to find evidence of companions around most Blasco stars, making this seem an unlikely universal explanation. The truth is, no single theory has managed to explain all the observed variations, leading many researchers to suspect the answer may be a subtle combination of several of these effects. The observational characteristics of these stars are a fingerprint of their internal chaos. When astronomers plot the light curve of a Blasco-affected Ara Lyrae star over many months, they don't see a simple, repeating pattern. Instead, they see a complex interplay of changes. The amplitude modulation is often the most obvious signature. The peaks and troughs of the light curve get taller and deeper, then shallower again over the course of the Blasco cycle. More subtle but just as important are phase shifts. The moment of maximum brightness might occur slightly earlier or later than predicted from the average period. In the most extreme cases, the shape of the light curve itself can appear distorted, becoming more rounded or more sharply peaked at different points in the long-term cycle. These are not random fluctuations. They are precise, repeating patterns of variation that are incredibly difficult to model mathematically because they involve non-linear dynamics, a branch of physics dealing with systems where outputs are not proportional to inputs, famously known for the butterfly effect. Modern astronomy, with its powerful automated sky surveys, has transformed this field from the study of a few curious examples to a statistical analysis of thousands. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Kepler Space Telescope have monitored dense star fields for years, identifying and cataloging countless variable stars. This vast dataset has revealed that the Blasco effect is not a rare oddity. It may affect a significant fraction of all Ara Lyrae stars. This sheer volume of data, however, presents its own challenge. How do you analyze the intricate light curves of tens of thousands of stars? This is where the global community of citizen scientists has stepped in to make a truly invaluable contribution. Through online platforms like Zooniverse, projects such as the Catalina Survey's Variable Star Recognition Program have enlisted the help of hundreds of thousands of volunteers. These amateur astronomers from around the world visually inspect light curves, classifying patterns and identifying the telltale signs of Blasco modulation, a task where the human eye for pattern recognition still outperforms automated algorithms. It's a beautiful collaboration between professional astrophysicists and curious citizens, all working together to solve a century-old cosmic mystery. There is a profound lesson in the stubborn persistence of the Blasco effect. It reminds us that even the most seemingly simple and well-understood objects in the universe can harbor deep, hidden complexities. A star that appears as a single point of light, pulsing with reassuring regularity, is in reality a maelstrom of competing forces, a complex engine of physics we are still learning to decode. Its rhythmic light is the end product of a delicate balance between gravity, pressure, nuclear fusion, and magnetism, a balance that can apparently waver in a long, slow dance we are only just beginning to perceive. This appreciation for hidden complexity perfectly sets the stage for our next stellar anomaly, where we will meet pulsating stars that abandon rhythm altogether, descending into truly chaotic and erratic behavior. Now we turn from the metronomic beat of Ara Lyrae stars to a different, more soulful rhythm in the cosmic symphony, the slow, deep breath of Mera variables. For centuries, these pulsating red giants have been the dependable grandfather clocks of the long-term variable star world. Named after their prototype, Mera itself, or Omicron Ceti, these stars swell and contract over periods stretching hundreds of days, their brightness rising and falling with a comforting, predictable regularity that has made them beloved by amateur and professional astronomers alike. Their pulsation is a fundamental part of their final act, a steady rhythm as they approach the end of their lives. But just as we think we understand their gentle cadence, a subset of these stars begins to behave erratically, throwing tantrums that defy their well-established cycles, suddenly dimming for no apparent reason or shifting their entire period, leaving astronomers scratching their heads and reaching for new theories. The historical record of Mera's own observations provides the perfect backdrop for this mystery. This star was first noted in 1596 by the Dutch astronomer David Fabricius, who saw it as a new star where none had been before, only to watch it vanish again. It was its rediscovery by Johannes Hevelius a few decades later that cemented its nature. He named it Mera, the Wonderful, for its astonishing changes. For over 400 years, its cycle has been meticulously documented, typically fluctuating between magnitude 3, easily visible to the naked eye, and magnitude 9, requiring a telescope over a period of about 332 days. This long history is what makes its occasional misbehavior so jarring. There are well-documented instances where Mera and stars like it have suddenly deviated from their script. They might experience a phase glitch, where the timing of their maximum brightness shifts unexpectedly, or they might undergo a dramatic, unpredicted dimming event, dropping in brightness far more than their standard light curve would allow. These are not minor fluctuations, they are fundamental breakdowns in the predictable machinery of the star. So what could cause such a dependable clock to suddenly lose time? Astrophysicists point to the incredibly complex and volatile internal environment of an aging giant star. One leading culprit is a thermal pulse. As a Mera variable nears the end of its life on the asymptotic giant branch, it undergoes periodic and violent instabilities in a shell of helium that surrounds its inert carbon-oxygen core. Every 10,000 to 100,000 years, this helium shell ignites in a brief but powerful flash of fusion. This sudden injection of energy sends a powerful shockwave through the star's interior, disrupting the delicate balance between gravity and pressure that drives its regular pulsations. It's like throwing a large rock into a calm, pulsating pond. The resulting waves completely distort the normal rhythm. Dr. Claudia Windemuth, who models these late stages of stellar evolution, explains, a thermal pulse is a seismic event for the star. It completely resets the star's structure and can alter its pulsation period, mass loss rate, and even its chemical composition for centuries. Another fascinating mechanism involves the star's own self-made shroud. Mera variables are prodigious producers of cosmic dust, blowing enormous amounts of processed material into space through powerful stellar winds. This dust is primarily composed of silicates and carbon compounds forged in the star's interior. Occasionally, a particularly dense and localized cloud of this dust could form right in our line of sight, temporarily eclipsing the star and causing a sudden, sharp dip in its observed brightness. From our perspective, it looks like the star has dramatically dimmed, but in reality, it's just momentarily hiding behind its own smoky exhaust. Furthermore, the presence of a previously unknown binary companion could also be a factor. The gravitational influence of a nearby star, perhaps a white dwarf or a main sequence star, could perturb the Mera variable's outer layers, subtly altering its pulsation period or triggering enhanced mass loss that manifests as irregular dimming. The key to unraveling these mysteries lies not in visible light, but in the infrared. While a Mera variable might be flickering unpredictably in the light our eyes can see, infrared telescopes can peer through the veils of dust to see what's really happening at the star itself. A famous case study involved the star R Leporis, also known as Hine's Crimson Star. This carbon-rich Mera variable is famous for its deep red color, caused by its extensive dust envelope. Observations with the Very Large Telescope Interferometer in Chile revealed that it wasn't pulsating symmetrically. Instead, it was surrounded by a dynamic, clumpy, and incredibly complex cloud of dust that was being ejected in spurts and asymmetrical plumes. This wasn't a smooth, steady wind. It was a chaotic, coughing mass loss directly linked to the star's erratic photometric behavior. The infrared data showed that the star itself was pulsating regularly, but its own ejected material was creating a variable obscuration that made its light output appear wildly irregular from our distant vantage point. This erratic behavior forces us to ask profound questions about the ultimate fate of these stars. Does a period of unusual instability signal that the star is nearing its final death throes? Could a particularly violent thermal pulse or a massive ejection of material be the precursor to the star shedding its entire outer envelope and transitioning into a planetary nebula with a white dwarf at its center? Or are these simply the normal, if infrequent, growing pains of an elderly star, hiccups that subside as it continues on its long, slow journey toward oblivion? The answers are crucial because Mera variables are major contributors to the chemical enrichment of galaxies, and understanding their behavior is key to modeling the life cycle of matter in the universe. Their unpredictable phases remind us that even in the seemingly peaceful final years of a star's life, there can be episodes of intense and dramatic change, a prelude to the truly spectacular finales we witness in stars that take variability to an entirely new, eruptive level. Yet if the erratic pulses of Mera variables represent a star's final, faltering breaths, our next anomaly showcases a celestial object in the midst of a full-throated, violent scream. We now enter the realm of the luminous blue variables, stars so massive, so unstable, and so spectacularly violent that they redefine the very meaning of stellar outburst. These are not the gentle swells of a red giant. These are cataclysmic eruptions on a scale that is almost incomprehensible, events where a single star can, in a matter of months, eject more mass than our entire sun contains. They are the supermassive stars that have reached a point of critical instability, and their struggle against their own immense power is one of the most dramatic shows in the cosmos. No story better illustrates the sheer, awesome power of an LBV eruption than the historical saga of Eta Carinii. In the year 1843, from our vantage point on Earth, a faint star in the southern constellation of Carina suddenly began to brighten. It didn't just twinkle a little more brightly, it underwent a paroxysmal explosion of light. Within a few years, it rocketed to become the second brightest star in the entire night sky, outshone only by Sirius despite being nearly 8,000 light-years away. This event, now known as the Great Eruption, was not a supernova. The star survived. Instead, it was a colossal tantrum, a hypergiant star violently expelling its own outer layers into space. By the time the light show subsided, Eta Carinii had blasted away material equivalent to at least 10 times the mass of our Sun, creating a vast, expanding cloud of gas and dust known as the Homunculus Nebula. This nebula, shaped like a vast cosmic peanut, is a permanent scar from that eruption, a tombstone for the material that was once part of the star itself. The significance of luminous blue variables extends far beyond their spectacular light shows. Astronomers now believe these eruptive giants represent a crucial and thankfully brief transitional phase in the life of the most massive stars. A star born with well over 100 times the mass of our Sun lives its life on the very edge of stability. After spending millions of years burning hydrogen in its core, it begins to evolve into a helium-burning supergiant. It is during this incredibly unstable period that it may enter the LBV phase. Here, the star is so luminous that its own light exerts a tremendous outward radiation pressure, pushing against the inward pull of gravity. It is balancing at the Eddington limit, the absolute maximum luminosity a star can achieve before radiation pressure overcomes gravity and begins to blow the star apart. Dr. Nathan Smith, an astrophysicist who has extensively studied these objects, describes them as stellar powder kegs, where the star's outer layers are so loosely bound by gravity that even a slight nudge from pulsations or internal instabilities can trigger an enormous outburst, effectively allowing the star to vent its excess energy and mass into space. This shedding of its hydrogen-rich envelope is what ultimately prepares the star for its next act, evolution into an even more extreme Wolf-Rayet star, a hot, bare core fusing heavier elements, or a direct collapse into a supernova. The mechanics behind these eruptions are a complex dance of forces we are still working to understand. The leading theory, known as the super-Eddington instability, posits that in the star's bloated outer layers, the radiation pressure can temporarily and locally exceed the force of gravity. This creates regions where the light itself is so intense it can literally push the stellar material outward, not in a steady wind, but in a violent, convective overturning. It's like a pot of water boiling over with tremendous force, rather than simply evaporating. This process can be aided by the star's own rotation, which flings material more easily from its equator, and by the presence of powerful magnetic fields buried deep within its interior, which can channel and accelerate the ejector. The result is not a spherical explosion, but often a bipolar outflow, creating the distinctive hourglass or lobe-shaped nebulae we see around stars like Eta Carinae. The properties of LBVs make them utterly unique celestial laboratories. They exhibit the highest sustained mass loss rates of any known type of star. Where our Sun loses a tiny fraction of its mass in a solar wind over billions of years, an LBV can eject a solar mass every 100 years during an active phase. Their temperatures and luminosities place them in a volatile region of the Hertzsprung-Russell diagram known as the S Doradus instability strip, named after another classic LBV in the Large Magellanic Cloud. Here, they don't just erupt, they also undergo less dramatic but still significant super outbursts, or giant eruptions, where their brightness can vary by several magnitudes over years or decades. Furthermore, they are often enshrouded in the complex nebulae of their own making, which act as a fossil record of their past violent episodes. While Eta Carinae is the most famous example, it is far from alone. Our galactic neighbor, the pinwheel galaxy M101, hosts its own famous LBV, a star catalogued as M101V1. This star underwent its own dramatic outburst in the early 2000s, suddenly becoming 1,000,000 times brighter than our Sun, and providing astronomers with a front-row seat to study the phenomenon in a galaxy 25 million light-years away. The Hubble Space Telescope has been indispensable in this research. Its sharp vision has resolved the intricate structures of the homunculus nebula around Eta Carinae in stunning detail, revealing vast lanes of dust, numerous shock fronts where ejected material collides, and even faint, fast-moving knots of gas that were shot out like bullets during the Great Eruption. These images are not just beautiful, they are data-rich maps that allow scientists to reconstruct the physics of the explosion, measuring the speeds, masses, and energies involved with unprecedented precision. One can't help but engage in a truly awe-inspiring thought experiment. Imagine for a moment what it would be like to witness an event like the Great Eruption from a safe, closer distance. Picture a world orbiting a star 100 light-years away from an LBV. One night, a new star appears in the sky, not as a faint twinkle, but as a brilliant second sun. Over the following months, it grows steadily brighter until it outshines your own star, casting sharp double shadows and turning night into day. The celestial spectacle would be both beautiful and terrifying, a constant reminder of the unimaginable forces at play in the universe. It would be a display of cosmic power so profound it would undoubtedly shape the culture, mythology, and science of any civilization that witnessed it. This journey through the explosive lives of luminous blue variables forces us to confront the raw, untamed power of the most massive stars. They are not serene beacons, they are volatile, evolving engines of creation and destruction, whose violent outbursts seed the surrounding cosmos with the heavy elements necessary for planets and life. Their existence is a frantic, brilliant prelude to an even more dramatic end, a supernova or even a hypernova that will one day scatter their remains across the galaxy. This understanding of stars pushing the very limits of physical law naturally makes us wonder about the very first stars to ever exist, objects that were not just massive but truly primordial, forged from the pristine elements of the Big Bang itself. But if the explosive fury of luminous blue variables represents the dramatic end of stellar life as we know it, we must now cast our gaze back to the very beginning, to a time before any metals, before any planets, before any of the familiar cosmic objects we see today. We are searching for the ultimate origin story, the first chapter in the Book of Stars, Population 3 Stars. This is not a class of star we can point our telescopes at and observe directly. They are entirely hypothetical, the ghosts of cosmic dawn, but their existence is a necessary and profound cornerstone of our understanding of the universe. These would have been the very first stars to ever ignite, blazing to life in a cosmos that was utterly dark, silent, and composed of only the two simplest elements, hydrogen and helium, the pristine ashes of the Big Bang itself. The nature of these primordial giants would have been unlike anything that has formed since. Cosmologists running sophisticated supercomputer simulations, like those led by Dr. Volker Brom at the University of Texas, paint a picture of stars of almost unimaginable scale and power. Without any heavier elements to help cool the collapsing gas clouds through radiation, the first stars could accumulate absolutely staggering amounts of mass before triggering fusion. Current models suggest that a typical population 3 star might have been anywhere from 100 to 1,000 times the mass of our Sun. They would have been monsters, titans of pure hydrogen and helium, and their lives would have been as brilliant as they were brief. Burning their nuclear fuel at a ferocious rate to support their incredible bulk, they would have lived for only a few million years, a cosmic blink of an eye, before meeting a violent end in colossal supernova that would literally rip them apart, scattering the first heavier elements into the void. This is their ultimate and most important legacy. They were the universe's first alchemists. The cores of these massive stars were the first furnaces to ever forge elements heavier than helium. The carbon, oxygen, nitrogen, and iron that are the fundamental building blocks of planets, life, and indeed every star that has come after. When they died, their cataclysmic explosions seeded the pristine intergalactic medium with these first metals, polluting the cosmos and forever changing the recipe for future star formation. This is precisely why they cannot exist today. The conditions of the early universe were unique. Once that first generation enriched the cosmos with even a tiny amount of metals, the process of star formation changed forever. Gas clouds could now cool more efficiently, leading to the formation of smaller, longer-lived stars like our Sun. The age of the primordial giants was over almost as soon as it began, but their influence echoes through every subsequent generation of stars, planets, and people. The central challenge for astronomers, then, is a profound one. How do you study something that has been extinct for over 13 billion years? The answer lies in the subtle, indirect signatures they left behind. One promising avenue is the search for their supernova. The death throes of a 200 solar mass star would be a spectacle unlike any supernova we see today. A hypothetical pair instability supernova that would be orders of magnitude brighter and would leave no remnant behind, completely disintegrating and scattering its entire contents into space. Astronomers are meticulously scanning the deepest images from the James Webb Space Telescope, looking for these uniquely bright and short-lived infrared transients in the most distant galaxies, a telltale sign of a first star death. Another method involves studying the oldest and most metal-poor stars in our own galaxy, like the famous SMSS J0313-67082.3. A star so devoid of iron it is thought to have formed directly from the material polluted by a single population 3 supernova. Its chemical fingerprint is a direct archaeological record of that first explosion. Furthermore, cosmologists are listening for the faintest echoes of their formation. The gravitational collapse of those first massive dark matter halos which pulled in the gas to form the first stars would have created ripples in space-time primordial gravitational waves. While far too faint for our current observatories to detect, future space-based detectors may one day tune into this faint hum from the dawn of time. Even the cosmic microwave background, the leftover radiation from the Big Bang, might hold subtle polarization patterns imprinted by the very first bursts of light from these stars as they began to reionize the neutral hydrogen that filled the early universe, slowly turning it transparent. One cannot help but be struck by the sheer, awesome power of that first sunrise. What would it have been like to witness it, not from a planet, for there were none, but from some impossible vantage point in the dark, empty void? After hundreds of millions of years of perfect blackness, a point of light would suddenly appear, not the gentle yellow of our sun, but a searing, actinic blue, tens of times hotter and millions of times brighter. It would be a solitary beacon in an endless night, a signal that the universe had finally awoken and begun its long journey toward complexity. That first star would have lived a short, lonely, and spectacular life, its death ensuring that it would never be alone again, seeding the cosmos with the potential for everything that was to come. This contemplation of the universe's first and most influential stars makes the behavior of our own modern sun seem almost placid by comparison, a stability that itself can become an anomaly when taken to its extreme. After witnessing the explosive ends of the universe's first stars, we arrive at a cosmic paradox that hits much closer to home, a puzzle not of terrifying power, but of unsettling quiet. Our own sun is a dynamic, living entity, its surface a churning canvas of magnetic activity. Every 11 years or so, it cycles through a period of intense sunspots, violent flares, and coronal mass ejections that can send storms of radiation racing toward Earth. This magnetic heartbeat is something we've come to expect from a middle-aged yellow dwarf star. So imagine the profound surprise when astronomers, sifting through data from missions like Kepler, began to find stars that look almost identical to our sun in size, mass, and temperature, but with one breathtaking difference: they are utterly, completely silent. These stars show no signs of a magnetic cycle, no sunspots marching across their surfaces, no flares, just a steady, unwavering, and frankly eerie calm. They have been dubbed flat activity stars, and their existence is quietly upending our understanding of how stellar dynamos work. The discovery of these celestial quiet neighbors was almost accidental. For decades, the study of stellar activity focused on the noisy ones, stars with pronounced cycles, clear starspot modulations, and dramatic flares. It was only with the long-term, ultra-precise photometric monitoring by the Kepler Space Telescope that astronomers could finally see the subtlest variations in a star's light. When researchers like Dr. Travis Metcalf of the Space Science Institute began to categorize thousands of Sun-like stars, they expected to find a spectrum of activity levels. What they didn't expect was to find stars that plotted not as a point on that spectrum, but entirely off it. Their light curves were flat, not in the sense of being perfectly constant, but showing none of the quasi-periodic variability that signals the rise and fall of magnetic features. Dr. Metcalf describes the moment of discovery as like listening for a heartbeat and hearing nothing but a steady tone. It was immediately clear that something fundamental was different about these stars. This discovery punches a hole right through the heart of our standard solar dynamo theory. This theory explains the Sun's magnetic cycle as a complex engine driven by two main ingredients, rotation and convection. The Sun's differential rotation, its equator spins faster than its poles, winds up and twists internal magnetic field lines, while the churning motion of convection in the outer layer helps bring those fields to the surface, creating the activity we see. It's a beautifully elegant model that has served us well, but a flat activity star presents a glaring contradiction. It has convection, it has rotation. So why no magnetic activity? Solar physicists are now forced to consider that the recipe might require a very specific and perhaps rare combination of these ingredients. Perhaps these quiet stars rotate much more slowly than our Sun, providing less energy to the dynamo. Maybe their interior structure is different, with a thinner or thicker convection zone that prevents the self-sustaining magnetic cycle from ever getting started. Or, most intriguingly, perhaps their magnetic fields are organized in a fundamentally different way, not in the chaotic, patchy manner that creates sunspots, but in a much smoother, large-scale, and stable configuration that is simply invisible to our current detection methods. The implications of this stellar silence extend far beyond theoretical astrophysics and into the very practical search for life beyond Earth. A star's magnetic activity is the primary driver of its space weather. Our Sun's flares and coronal mass ejections, while creating beautiful aurorae, also pose a significant threat to technology and, in a worst-case scenario, could strip away a planet's atmosphere over time. A flat activity star would offer a radically different environment. Any planets in its habitable zone would be bathed in a constant, gentle starlight, free from the violent radiation storms that rack our own solar system. This sounds like an astrobiologist's dream, a truly stable, peaceful haven for life to arise and evolve. Missions like the upcoming planetary transits and oscillations of stars Mission, or Plato, are specifically designed to find Earth-sized twins around Sun-like stars, and the activity level of the host star will be a critical factor in assessing a planet's potential for habitability. We can already point to real-world examples that hint at this possibility. One of the most famous quiet stars is actually one of our nearest neighbors, Tau Ceti, located just 12 light-years away. It's a G-type star very similar to our Sun, but observations have consistently shown it to have remarkably low magnetic activity. It's known to host a system of several planets, some of which are rocky worlds orbiting within its habitable zone. While we don't yet know if these planets have atmospheres or signs of life, the calm nature of their sun is a powerful point in their favor. It suggests that any potential life there wouldn't have to worry about their star suddenly unleashing a flare that could wipe out their ozone layer. The search for an Earth twin isn't just about finding a planet the right size at the right distance. It's also about finding it around the right kind of star. A quiet, stable sun might be the most important ingredient of all. Yet, this idyllic picture comes with its own set of fascinating questions. Could a star be too quiet for life? Our own sun's magnetic activity, for all its dangers, might play a crucial role in the development of life on Earth. Some theories suggest that the electrical discharges from solar storms could have provided the energy needed to jump-start the formation of complex organic molecules in Earth's early atmosphere. Furthermore, the gentle pressure of the solar wind helps form the heliosphere, a protective bubble that shields our solar system from the harsh interstellar radiation of deep space. If a star had virtually no solar wind, would its planets be more exposed to galactic cosmic rays? The relationship between a star and its planets is a complex, two-way street, and the discovery of these magnetically silent suns opens up a whole new frontier in understanding what truly makes a system habitable. This contemplation of stellar stillness makes the behavior of our next anomaly seem all the more extreme, as we pivot to stars that are the absolute antithesis of calm. After contemplating the profound quiet of magnetically silent stars, we are thrust into a cosmic environment that is anything but calm, a realm where stars spin with such ferocious velocity that they defy their own spherical nature, stretching themselves into dizzying oblate spheroids on the very brink of self-destruction. Picture a star not as a serene, placid sphere, but as a frantic cosmic top, spinning so rapidly that its equator bulges outward against the pull of gravity, while its poles flatten under the immense centrifugal force. This is not a hypothetical scenario, it is the reality for a class of extreme rotators, and perhaps no star exemplifies this better than Achernar, the brightest star in the constellation Eridanus. Observations using advanced techniques like optical interferometry have revealed that Achernar is one of the flattest stars ever measured, with its equatorial diameter more than 50% larger than its polar diameter. It spins at a breathtaking 300 kilometers per second, so fast that its surface gravity is significantly weaker at the equator, creating a star that looks less like a perfect sphere and more like a blue pumpkin hanging in the void. Measuring such incredible rotation requires a blend of clever techniques and cutting-edge technology. The primary method is spectroscopy, specifically analyzing a phenomenon called Doppler broadening. As a star spins, one side of its hemisphere is rotating toward us, blue-shifting its light, while the other side is rotating away, red-shifting it. This smears out the sharp absorption lines in the star's spectrum, making them appear wider and fuzzier. The broader the line, the faster the star is spinning. But to truly understand the star's shape, as in the case of Achernar, astronomers turn to interferometry. This technique combines the light from multiple telescopes spread apart, effectively creating a virtual telescope as large as the distance between them. This allows for an incredible resolution, enough to not just detect the star as a point of light, but to actually image its distorted shape and measure its oblateness directly. It's a stunning achievement, allowing us to see the tangible effects of physics operating at its most extreme limits. The implications of such rapid rotation extend far beyond a star's appearance. They fundamentally alter its internal workings and its ultimate fate. The furious spinning creates a powerful engine of internal mixing. In a slowly rotating star like our Sun, the core and the envelope are largely separate with distinct layers. But in a rapid rotator, the centrifugal force stirs the interior like a colossal blender, dragging material from the hydrogen-burning core up toward the surface and pulling fresh fuel down from the envelope into the core. This process dramatically extends the star's lifespan by replenishing its nuclear furnace, and it also changes the chemical composition of its outer layers. Elements normally hidden deep in the core, like nitrogen and helium, are dredged up and revealed at the surface, creating strange and chemically peculiar stars that wouldn't exist without this internal churning. This altered nucleosynthesis means that when these stars finally die, they will eject material into space with a very different chemical signature, influencing the composition of future generations of stars and planets. This leads us to a fundamental puzzle in stellar astrophysics known as the angular momentum problem. A star forms from the collapse of a massive, slowly rotating cloud of gas and dust. As the cloud contracts, the conservation of angular momentum dictates that its spin should increase dramatically, just as an ice skater spins faster when they pull their arms in. Simple calculations show that if all this primordial spin were retained, every newborn star should be rotating at breakneck speeds, tearing itself apart before fusion could even begin. Clearly, this doesn't happen. Stars like our Sun, middle-aged and sedate, have found a way to shed this excess spin. The mechanism is a stellar wind coupled with a magnetic field. The Sun's magnetic field acts like an anchor, locking into its ionized wind and effectively applying a brake, transferring angular momentum out into space and slowing the rotation over billions of years. This is why we see a clear trend. Younger stars spin rapidly while older stars have slowed down. The existence of ancient, fast-spinning stars therefore presents a paradox, suggesting they have somehow avoided this magnetic braking, perhaps through a weak magnetic field or a unique history. So how does a star become a rapid rotator later in life, defying the typical trend of spinning down? Nature has two primary mechanisms for giving a star a second wind, quite literally. The first is accretion. In a close binary system, a star can pull material from its companion. This incoming material doesn't just add mass, it also carries angular momentum, effectively spinning the star up. It's like pushing a merry-go-round to make it go faster. The second, and even more dramatic mechanism, is stellar merger. If two stars in a binary system eventually coalesce, the resulting single star will have the combined angular momentum of its progenitors, often leading to an incredibly rapid spin. This is thought to be the origin of many blue stragglers, those seemingly youthful stars in old clusters, as the merger of two older stars creates a new, massive, and rapidly rotating object that stands out from its sedate neighbors. Among the most fascinating and beautiful products of rapid rotation are the classic B stars. These are B-type stars, hot and luminous, that are rotating at a significant fraction of their break-up speed, typically at least 75%. Their rapid spin is the direct cause of their most distinctive feature, a dense equatorial disk of ejected gas. Centrifugal force becomes so strong at their bulging equator that it overcomes gravity, flinging material off into space. This creates a circumstellar disk of hydrogen gas that is visible in emission lines in the star's spectrum, the E in B star. These disks are dynamic and changing, sometimes dissipating and later reforming, making B stars variable and unpredictable. They are cosmic whirligigs, spinning so fast they are constantly shedding their own skin, creating a shroud of their own ejected material that astronomers can study to understand the complex physics of mass loss. To grasp the truly extreme end of this phenomenon, we must look to the most massive stellar nurseries. In the Tarantula Nebula within the Large Magellanic Cloud, astronomers have found some of the fastest spinning stars ever recorded. One of the most spectacular is VFTS 102, a massive star clocked at a staggering 600 kilometers per second. At this speed, it is rotating at approximately 90% of its critical velocity, the point where centrifugal force would equal gravity and the star would tear itself apart. This star is not just spinning, it is a cosmic razor's edge, a testament to the most violent forces of stellar formation. Its existence suggests it may have been spun up by accreting material from a binary companion that later went supernova, potentially ejecting it from its cluster as a runaway star. It is a furious, solitary spinner, hurtling through space while racing toward its own inevitable demise. The fate of these stellar speed demons is as violent as their lives. The intense internal mixing caused by their rotation changes the course of their evolution, potentially allowing them to burn brighter and longer than their sedentary siblings. However, this altered evolution also points toward a spectacular and rare death. Some theorists suggest that the very fastest rotating massive stars, particularly those that retain their spin until their final moments, are prime candidates for producing long-duration gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. These cataclysmic events are thought to be the birth cries of a newly formed black hole, accompanied by jets of material shooting out at nearly the speed of light. The rotation provides the necessary energy to power these jets. Alternatively, if the star's core retains enough angular momentum as it collapses, it could form not a black hole, but a magnetar, a neutron star with a magnetic field of unimaginable intensity, itself a rapidly spinning remnant of a violent life. One cannot help but stare into the night sky and wonder, what is the absolute limit? How fast can a star truly spin before physics itself says no more? The answer lies in the delicate balance between gravity's inexorable inward pull and the centrifugal force's desperate outward push. The theoretical limit is that critical velocity, a number that depends on the star's mass and size. But reaching it is another matter. As a star spins faster, it bulges, and its equator moves farther from the center, which actually lowers the rotational speed needed to tear it apart. It's a self-regulating system. Nature finds ways to shed angular momentum through mass loss, often by flinging material from the equator to form a disk, effectively acting as a safety valve. This dynamic equilibrium ensures that while stars can dance on the edge of stability, they rarely cross the final threshold into total disintegration. This exploration of solitary stars spinning at the brink of chaos naturally makes us ponder an even more complex dance, the intimate and often perplexing gravitational embrace of two stars locked in a binary system, where their spins become intertwined with their orbit. Now, imagine a stellar relationship so intimate that the very idea of two separate stars begins to break down. We are entering the realm of contact binaries, a celestial dance so close that the participants no longer maintain their own personal space. They share everything, including their atmospheres, in a single, swirling, common envelope. This isn't just two stars orbiting each other. It's a cosmic merger in slow motion, a gravitational embrace so tight that the stars become tidally distorted into teardrop shapes, connected by a bridge of superheated plasma. They are no longer distinct entities, but a single, peanut-shaped system, a shared stellar identity that represents one of the most extreme and fascinating phases of binary evolution. To understand this phenomenon, we can look to a classic example, a star system that has become the archetype for this entire class, W Ursae Majoris. Located about 160 light-years away, this system consists of two stars, a slightly larger and cooler one and a smaller, hotter companion, locked in an orbit so close they complete a full circle in just under 8 hours. Their gravitational pull on each other is so immense that they are stretched into ellipsoidal shapes, their outer atmospheres having long since spilled out and merged into a single, gaseous shroud that envelops them both. From a distance, it doesn't look like two stars, but one single, pulsating object. The more massive star transfers material to its partner, but in this shared environment, the concept of ownership is blurred. Energy and matter flow continuously between them in a complex, convective dance that keeps their surfaces at almost identical temperatures, a state of thermal equilibrium that is unique to these contact systems. The significance of these cosmic unions extends far beyond their peculiar appearance. Astronomers like Dr. Joanna Molender-Zakovich, who studies stellar astrophysics, point out that contact binaries represent a critical, and often final, stage in the life of a close binary system. They are the calm before a potential storm, a temporary equilibrium in a long process of orbital decay. The constant rubbing of their atmospheres within the common envelope creates a dynamic friction, slowly sapping the system's orbital energy. This process inexorably draws the two stellar cores closer together, setting the stage for a future of dramatic possibilities. They are living laboratories for studying complex hydrodynamics and energy transfer on a scale we could never hope to replicate, allowing us to test our theories of how matter behaves under the most extreme gravitational conditions. Identifying these systems is a task perfectly suited to the age of all-sky surveys. The primary method is through their highly distinctive light curves. Unlike detached eclipsing binaries, which show two distinct, sharp dips in brightness as each star passes in front of the other, the light curve of a contact binary is smooth and continuously variable. Because the stars are so distorted and connected, there is no moment when one is fully hidden. Instead, the combined light of the system changes in a smooth, sinusoidal wave as the differently shaped sides of the stellar pair rotate in and out of our view. This continuous variation is the unmistakable signature of this intimate stellar dance, a beacon for automated telescopes like those used in the all-sky automated survey to find and catalog thousands of such systems across our galaxy. The ultimate fate of these conjoined stars is what makes them truly consequential to the broader cosmos. Many are thought to be the direct progenitors of the most dramatic stellar explosions we know of. One pathway leads to a red nova. As the two cores spiral ever closer within their shared envelope, they can eventually merge. This merger triggers a tremendous outburst of energy, causing the star to brighten dramatically by thousands of times, creating a luminous red nova, a distinct class of explosion that is less energetic than a supernova but far more powerful than any nova. The famous object V1309 Scorpii, which flared up in 2008, is a prime candidate for such a stellar merger event. Another, even more critical pathway exists for systems where at least one of the stars is a white dwarf. If the merger involves a white dwarf and it accretes enough mass to reach the Chandrasekhar limit, it can trigger a cataclysmic type Ia supernova, the very same kind we use as standard candles to measure the expansion of the universe. The contact binary phase could be the final chapter for many such systems before they annihilate themselves in a titanic blast. There is a fascinating historical anecdote that highlights how these systems challenge our intuition. For a long time, theorists struggled to understand how the deep common envelope could remain stable. Why didn't it simply dissipate into space? The answer lies in a delicate balance of forces. The envelope is bound to the entire binary system, not to either star individually. The orbital motion of the stellar cores within this envelope helps to stabilize it, while the immense gravity of the duo keeps the gas from escaping. It's a precarious, self-regulating structure, a cosmic figure 8 of plasma that persists for millions of years, testing our models of stellar structure and fluid dynamics to their absolute limits. One cannot help but try to visualize the view from a hypothetical planet orbiting such a system. The sky would be dominated by a single, vast, irregular luminary, a glowing hourglass of connected suns, its surface boiling with constant activity as rivers of plasma stream between the two cores. Day and night would be dictated by the rotation of this bizarre, single object, its light constantly shifting in brightness and color in a rhythm that echoes its orbital period. It would be a breathtaking and utterly alien panorama, a constant reminder of the fluid and dynamic nature of stars, and a preview of the even more complex gravitational dances that occur when not two, but three or more stars decide to orbit in a single, chaotic system. Now, we venture from the intimate embrace of contact binaries into a far more complex and chaotic gravitational arena, the triple star system. While a binary system is a stable dance, a trio is often a precarious balancing act, a celestial game of musical chairs where the slightest nudge can lead to ejection, collision, or a dramatic reshuffling of partners. This is the domain of gravitational dynamics at its most pure and untamed, where the simple, elegant laws of Newtonian physics give rise to astonishingly complex and unpredictable behavior. In these systems, stars don't just orbit, they interact, they perturb, they influence, and they ultimately decide each other's fates in a cosmic drama that can play out over millions of years. To grasp the delicate nature of these systems, we can look at one of our very nearest neighbors, the Alpha Centauri system. For many, it's known as a binary pair, Alpha Centauri, A and B, orbiting each other roughly every 80 years at an average distance comparable to that between the Sun and Uranus. But this is a triple system. Circling this central pair from a vast distance of over 13,000 astronomical units is Proxima Centauri, a faint red dwarf and the closest known star to our Sun. The immense separation keeps Proxima gravitationally tethered but largely unaffected by the intricate dance of the inner binary. This hierarchical structure, a close binary with a distant third companion, is nature's preferred way of organizing triple systems to achieve a semblance of stability. But not all triples are so orderly. When the orbits are tighter and less hierarchical, the system can become a ticking time bomb. The prevalence and importance of these multiple systems cannot be overstated. Dynamicists, astrophysicists who specialize in orbital mechanics estimate that a majority of stars in the galaxy might actually be part of binary or multiple systems. Our own single sun could be the exception rather than the rule. This makes understanding the long-term evolution of triples absolutely fundamental to astrophysics. They are natural laboratories for testing our theories of gravity beyond the simple two-body problem. By studying them, we learn how stars exchange energy and angular momentum, how they migrate within clusters, and what kinds of exotic endpoints are possible from these complex interactions. As Dr. Nathan Lee, an expert on stellar dynamics, often explains, a stable triple is a beautiful example of orbital harmony, but an unstable one is a factory for producing cosmic fireworks and runaway stars. One of the most fascinating engines of chaos within a stable hierarchical triple is a gravitational phenomenon known as the Kozai mechanism, or Kozai-Lidov oscillations. Imagine the distant third star acting as a constant, gentle tug on the inner binary pair. This persistent gravitational influence doesn't just pull, it torques. Over long timescales, it can cause the eccentricity of the inner binary's orbit to oscillate wildly. Their path around each other can shift from nearly circular to highly elongated and back again, all while the tilt of their orbital plane slowly changes. This mechanism provides a powerful way to dramatically alter orbits without any direct contact, simply through the subtle, cumulative effect of gravity. It's a process that has profound implications, potentially driving binary stars to merge, pushing planets into their suns, or explaining the bizarrely tilted orbits of some objects in our own solar system. The cosmos provides us with several famous examples that illustrate the diversity and drama of triple systems. Consider Polaris, the North Star. For centuries, it was thought to be a single, steady beacon. We now know it is a complex triple system. Polaris A is a supergiant orbited by a very close companion, Polaris AB, which was only directly imaged by the Hubble Space Telescope in 2006. Further out, a third star, Polaris B, orbits the main pair. Then there's the demon star, Algol, in the constellation Perseus. Its name comes from the Arabic for the demon's head, and its dramatic eclipses, which visibly dim its light to the naked eye every few days, have been observed for centuries. Algol is actually a triple system where the inner pair is a tight binary, and their eclipses are choreographed by the gravitational influence of a third star orbiting them both. This system is a classic example of how a third body can stabilize certain configurations while simultaneously driving complex interactions. To truly understand the potential for violence within these systems, astrophysicists turn to sophisticated n-body simulations. By coding the laws of gravity and setting 3 stars in motion with different initial positions and velocities, they can watch the drama unfold in accelerated time. Many simulations end predictably. The lightest star is often ejected from the system entirely, hurled into interstellar space at high velocity to become a runaway star, much like the hypervelocity stars we discussed earlier. The remaining 2 stars, now with an altered and tighter orbit, are left behind as a binary. In other, more chaotic scenarios, the orbits of the 3 stars can become so intertwined that they eventually lead to a close encounter and a direct collision or merger, creating a single, more massive star, a potential blue straggler, in a flash of incredible energy. These simulations show that triple systems are a key origin point for many of the stellar anomalies we find scattered throughout the galaxy. This naturally leads to a captivating and complex question. Could planets exist in such a tumultuous environment? The traditional view of a habitable zone, a narrow region around a single star where liquid water could exist, becomes almost comically complex in a triple system. A planet would be subject to the changing gravitational pulls of 3 different suns and would receive light and heat from multiple, varying sources. Its orbit could be severely perturbed over time, potentially being flung out of the system entirely or sent crashing into one of its stars, and yet, against all odds, we have found them. The Kepler telescope discovered a planet orbiting Kepler 16.4, a system with 3 stars. The planet orbits the inner binary, which is itself orbited by a third star. While the planet's environment would be bizarre, with sometimes double sunsets and varying levels of illumination, its discovery proves that planets can and do form in these chaotic gravitational environments. It expands our imagination of where life might possibly take hold, in skies filled with multiple suns tracing complex paths through the heavens. This realization that planets can persist in such complex systems makes the next discovery all the more baffling, not a problem of complex orbits, but of disks that are spinning in entirely the wrong direction. Just when we think we understand the orderly process of planet formation, a spinning star surrounded by a flat, swirling disk of gas and dust all moving in the same harmonious direction, the universe delivers another breathtaking curveball. Imagine a newborn star spinning peacefully in the void, and around it, a vast pancake-shaped disk of material from which planets will eventually coalesce. Now imagine that entire disk is spinning backward. It's a cosmic absurdity, like watching a gear turn clockwise while every tooth inside it rotates counterclockwise. This is the reality of stars with retrograde disks, a discovery so counterintuitive it forces us to question the very first steps of how solar systems are born. The revelation of these misaligned systems is a triumph of modern observational technology, particularly the power of the Atacama Large Millimeter/Submillimeter Array, or ALMA, high in the Chilean desert. ALMA doesn't see visible light, it sees the faint glow of cool dust and gas in the millimeter wavelength. This allows it to peer into the very hearts of these planet-forming disks. By meticulously mapping the subtle Doppler shifts in the light emitted by the gas, seeing which parts are moving toward us and which are moving away, astronomers can create a detailed velocity map of the entire disk. It was through this painstaking process that teams began to find disks where the motion was completely inverted relative to the spin of their central star. Dr. Eric Jensen, an astronomer who has studied these systems, captured the community's astonishment, noting, "It's about the last thing you would expect to find." The basic picture of a star and its disk forming together from a single, collapsing, rotating cloud predicts they should all be spinning the same way. Finding ones that aren't means our basic picture is incomplete. The implications of this discovery are profound, striking at the heart of protoplanetary theory. A retrograde disk isn't just a quirky oddity. It's a direct challenge to the standard model of star formation, which assumes the conservation of angular momentum from a single, coherent cloud. If the disk and the star are misaligned, especially by a full 180 degrees, it means that the material in the disk could not have come from the same smooth collapse that formed the star itself. Something must have happened to flip the disk or the star after their initial formation. This points to a much more chaotic and dynamic early history for planetary systems, where gravitational interactions and external influences play a far greater role than we ever imagined. So how does a star end up with a disk that spins the wrong way? Experts have proposed several captivating scenarios, each more dramatic than the last. The leading theory involves a stellar flyby, a gravitational hijacking by a passing star. In the dense environment of a young star cluster, close encounters are not uncommon. If another star passes by on a tilted or retrograde orbit, its gravity could violently strip material from the outer parts of a protoplanetary disk and fling it into a new, misaligned orbit around the host star. It's a cosmic robbery that leaves behind a disk of stolen goods spinning in the opposite direction. Another compelling idea points to the complex role of magnetic fields. If the magnetic field of the young star is misaligned with its rotation axis, it could torque the inner regions of the disk, effectively warping it over time and potentially flipping its orientation through a complex process of magnetic braking and friction. This would be an internal revolution rather than an external attack. The way a retrograde disk interacts with its star is fundamentally different and has dramatic consequences for any potential planets trying to form within it. The magnetic fields that launch powerful jets from the poles of young stars, for instance, would be interacting with a disk that is moving against them, potentially weakening those jets or altering their structure. Furthermore, the so-called hot Jupiter planets, gas giants orbiting extremely close to their stars, are thought to migrate inward through interactions with the disk. If that disk is retrograde, the migration process would be completely different, potentially explaining the bizarre and highly tilted orbits of some exoplanets. A planet forming in a retrograde disk would naturally inherit that backwards motion, meaning it would orbit its star in the opposite direction to the star's spin. Our very own solar system, with all its planets orbiting in a prograde, aligned fashion, might be the exception rather than the rule. We can see these theories in action by looking at specific celestial examples. The star HD 100,546, for instance, a young B star about 350 light-years away, has been intensely studied for its complex disk structure. ALMA observations have revealed not a simple flat disk, but a structure with multiple rings and gaps, hinting at the presence of forming planets. Some analyses suggest the inner disk may be significantly warped, and while not fully retrograde, it shows how magnetic fields or planetary perturbations can severely misalign different parts of a planetary nursery. An even more compelling case is the System du R44, located in the Ophiuchus star-forming region. Here, observations strongly indicate the disk is rotating in a direction that is not just tilted, but truly retrograde compared to the star's spin. It stands as one of the clearest and most baffling examples of this phenomenon. There's a wonderful anecdote from the early days of this research that highlights just how surprising these finds were. When the first data suggesting a retrograde disk was presented at a conference, it was initially dismissed by many as an error in interpretation or a calibration artifact. The result was so antithetical to the established paradigm that the default assumption was that the scientists had made a mistake. It was only after multiple independent teams, using different telescopes and techniques, began to confirm similar misalignments in other systems that the astronomy community fully accepted the reality of this strange anomaly. It was a classic example of a scientific discovery that was too strange to be believed at first, but too persistent to be ignored. This discovery inevitably expands our imagination of what alien solar systems might be like. If retrograde disks are not exceedingly rare, then retrograde planets cannot be either. Picture a world in such a system. Its sun would rise in the west and set in the east. The mechanics of its seasons and climate would be utterly unfamiliar, governed by a star that rotates in the opposite direction to the planet's orbit. How many of these backwards worlds are out there? The search for them is now a key part of exoplanet astronomy, and each one found is a testament to the violent and chaotic processes that govern the birth of planets. This realization that a star's most fundamental features can be so easily flipped by external forces makes the next category of anomaly seem almost inevitable. Stars that don't just have misaligned disks, but that themselves are behaving in the most inexplicable way, flickering and dimming as if something is passing in front of them that simply shouldn't be there. Yet, just as we begin to map the chaotic gravitational dances that shape star systems, we encounter a mystery that defies all known choreography. A star whose light doesn't just pulse or vary, but vanishes in dramatic, inexplicable dips that have left even the most seasoned astronomers grasping for answers. This is the enigma of KSE 8462852, more famously known as Boyajian star, or the star that launched 1,000 theories, including one so audacious it sparked a global conversation about intelligent life beyond Earth. The story begins with the Kepler Space Telescope, a mission designed to find planets by detecting the gentle, periodic dimming they cause as they transit their host stars. Kepler monitored over 150,000 stars with relentless precision, and in that vast sea of data, one star stood out not for its regularity, but for its breathtaking irregularity. While other stars showed the predictable, shallow dips of orbiting planets, this one displayed drops in brightness so deep, so erratic, and so bizarre that they simply didn't fit any known category of stellar behavior. The initial discovery was made not by a lone astronomer, but by a group of citizen scientists participating in the Planet Hunters project, who flagged the star's light curve as bizarre and interesting, little knowing they had just opened a Pandora's box of cosmic speculation. The significance of this star's behavior cannot be overstated. It forced the astronomical community to confront a fundamental question. When you see something in the sky that makes no sense, what is the process for figuring it out? Do you first exhaust every possible natural explanation, no matter how contrived, or do you allow yourself, even cautiously, to consider the possibility of an artificial origin? This is the razor's edge that Boyajian star placed us on. The lead author of the paper describing it, Dr. Tabitha Boyajian, now at Louisiana State University, famously stated that the light curve was something you would expect if an alien civilization built a megastructure around the star. While she and her colleagues were careful to present numerous natural hypotheses, that single, stunning comparison captured the public's imagination and ignited a firestorm of debate that reached far beyond academic journals and into the very heart of our culture. So what exactly does this star do that is so strange? Its light curve is its fingerprint of mystery. Unlike the clean, symmetrical U-shaped dips of a planet transit, Boyajian's star exhibits drops that are precipitous and asymmetrical, with some plunges removing a staggering 22% of the star's light. These are not the tiny 1% shadows cast by Jupiter-sized worlds. These are eclipses on a colossal scale. Furthermore, the dips are completely aperiodic. They do not repeat on a regular schedule. There might be a cluster of dramatic dimming events over a few days, followed by years of perfect quiescence, then another single, deep dip out of nowhere. The duration of these events also varies wildly, from a couple of days to over a week. This combination of depth, asymmetry, and irregularity is what makes the phenomenon so exceptionally difficult to explain with standard astrophysics. It suggests a transiting object, or more likely a collection of objects, that is both enormous and non-uniform, with a complex structure that blocks light in a way unlike any simple spherical body. The scientific community responded to this puzzle with a fascinating array of natural hypotheses, each trying to explain the data without resorting to extraterrestrial engineers. One of the earliest and most favored ideas involved a massive swarm of comets. The theory proposed that a family of exocomets, perhaps disturbed by the gravitational influence of a nearby star, had been pulled into a highly elliptical orbit that brought them close to Boyajian's star. As they swung near the star, their icy nuclei would sublimate, releasing enormous amounts of dust and debris that could form a giant, ragged cloud capable of blocking a significant amount of starlight. The irregular timing of the dips could be explained by the chaotic and constantly changing nature of such a swarm. Other theories pointed to circumstellar material, a thick, warped, and dusty disk of planet-forming debris that was somehow misaligned with the star, creating dense clumps that periodically passed in front of it. Some even suggested intrinsic stellar variability, proposing that the star itself was going through a unique and poorly understood phase of magnetic activity that caused huge starspots to form, although the sheer depth of the dimming makes this unlikely. The follow-up observations launched a new era of multi-wavelength astronomy focused on a single, enigmatic point of light. Teams across the globe pointed every available instrument at Boyajian's star, from the infrared vision of NASA's Spitzer Space Telescope to the giant radio dishes of the Green Bank Telescope, which listened for any potential artificial signals. The results were a mix of tantalizing clues and dead ends. Crucially, the dimming was found to be more pronounced at blue wavelengths than at red ones. This chromatic effect is a classic signature of dust. Smaller dust particles scatter blue light more effectively than red. This finding dealt a significant blow to the solid megastructure idea, as an alien-built object would likely block all wavelengths of light equally. However, it perfectly supported the comet swarm or dusty debris disk hypotheses. Furthermore, infrared observations did not show the excess heat that would be expected from a large, absorbing structure re-radiating the star's energy, again pointing toward a natural, dusty explanation. Yet, the precise nature and origin of that dust remained, and still remains, frustratingly elusive. This entire investigation highlights the increasingly vital role of citizen science in modern astronomy. The initial detection of Boyajian's star's bizarre behavior was made by volunteers, ordinary people around the world sifting through Kepler's public data from their home computers. This was not a fluke. Platforms like Zooniverse have empowered a global army of amateur scientists to perform tasks that are still difficult for algorithms, such as pattern recognition in complex light curves. Their collective effort allows professionals to identify the most promising and peculiar targets in vast datasets, effectively crowdsourcing the initial stage of scientific discovery. The story of Boyajian star is a powerful testament to this collaboration, proving that the next great cosmic mystery might be uncovered not just in a university lab, but by an curious individual halfway across the world. The reflective question this star forces us to ask is perhaps the most profound in all of science. How do we distinguish the natural from the artificial? What is the threshold of evidence? Boyajian star taught us that the scientific method, at its best, is a process of relentless elimination. We must first build and test every conceivable natural model, and only if all of them fail spectacularly should we entertain more exotic possibilities. It is a safeguard against our own biases and a testament to the principle that extraordinary claims require extraordinary evidence. While the dusty explanations currently hold sway, the case is not entirely closed. The star continues to be monitored, and each new dip provides more data. It stands as a permanent reminder that our galaxy is still full of surprises, and that some of its most common inhabitants, ordinary stars, can still behave in ways that challenge our imagination and force us to question everything we think we know. This lingering mystery of erratic dimming naturally draws our attention to another class of stellar outliers, those that don't just fade mysteriously, but erupt with sudden and terrifying violence. Yet if the mysterious, deep dimming of a star like Boyajian's represents a passive, obscuring anomaly, our next subject showcases a star's active, furious, and terrifying power. We now turn from the strangely quiet to the catastrophically loud, from something blocking a star's light to the star itself unleashing a light so violent it can redefine the meaning of a bad day in a planetary system. Our own sun is capable of impressive tantrums, solar flares that disrupt communications and paint our skies with aurorae. But these events are mere firecrackers compared to the cosmic detonations known as superflares. These are stellar outbursts that can release energy equivalent to 1 billion megaton bombs, events thousands of times more powerful than anything recorded in our solar system, and they are being detected on stars that look disconcertingly similar to our own. The discovery that sun-like stars can produce such apocalyptic eruptions came as a profound shock to astrophysicists. For a long time, it was assumed that superflares were the exclusive domain of active, young, or magnetically extreme stars like red dwarfs or rapidly spinning giants. That comfortable assumption was shattered by data from planet-hunting telescopes like Kepler and TESS. While their primary mission was to find new worlds by watching for the gentle dip of a transiting planet, they also became incredible observatories for stellar variability. They monitored the brightness of hundreds of thousands of stars with exquisite precision, and in that data, researchers began to find startling spikes. On seemingly ordinary, middle-aged G-type stars' solar twins, the light curve would occasionally, and without warning, spike dramatically upward in a matter of minutes, then slowly decay over hours or days. These were not subtle flickers, these were monumental surges of energy. Dr. Yuta Natsu of the University of Colorado Boulder, a leading researcher in this field, summarized the findings succinctly. Our study shows that superflares are rare events, but that they are possible on stars like our Sun. This should make us reconsider the long-term stability of our own planetary environment. The engine behind these colossal explosions is the same fundamental process that powers a solar flare, just scaled up to an almost unimaginable degree: magnetic reconnection. On any star, magnetic field lines arc up from the surface, often tracing the paths of sunspots. These lines can become twisted, stressed, and tangled over time. When the tension becomes too great, the field lines snap and reconfigure into a more stable state. a process that releases a tremendous amount of stored magnetic energy in the form of light, heat, and a torrent of accelerated particles. The difference between a solar flare and a superflare is one of sheer magnitude and magnetic complexity. Solar physicist Dr. Kazunari Shibata explains that superflare stars likely possess much stronger and more complex magnetic fields than our Sun, perhaps driven by much faster rotation or a more powerful internal dynamo. It's the difference between the static spark from a doorknob and a bolt of lightning from a supercell thunderstorm. The basic physics is the same, but the energy release is in a completely different league. The statistical data from Kepler and TESS has been nothing short of revolutionary, providing our first large-scale sensors of these violent events across a wide range of stellar types. Kepler's long, continuous stares at single patches of sky allowed it to catch these rare but spectacular outbursts. The numbers are staggering. While superflares are more common on fast-spinning, magnetically active young stars, the surveys confirmed that they do indeed occur on slower-moving, sun-like stars once every few thousand years. The energy released in these events is measured in ergs, a unit of energy astronomers favor. A typical, powerful solar flare might release around 10 to the 32nd power ergs. The superflares detected on solar twins have been recorded with energies up to 10 to the 35th power ergs, and on the most active stars, the true monsters have been observed, flares releasing a staggering 10 to the 38th power ergs. That is 10 million times more energetic than the largest solar flare ever recorded. The amount of energy is incomprehensible, enough to power human civilization at its current rate for hundreds of thousands of years, released in a single stellar heartbeat. To understand the potential consequences, we need only conduct a terrifying thought experiment right here in our own solar system. We have actually experienced a taste of a near superflare event back in 1859. It's known as the Carrington event, named after the British astronomer Richard Carrington, who witnessed the intense white light solar flare that preceded it. What followed was a coronal mass ejection of such power that it slammed into Earth's magnetosphere, inducing currents so strong that telegraph systems, the advanced technology of the day, failed spectacularly. Operators received shocks, telegraph paper caught fire, and orrery were seen as far south as the Caribbean. If a storm of that magnitude happened today, the results would be catastrophic. It would likely fry satellites, induce destructive currents in power grids that could lead to continent-wide blackouts lasting months or years, and cripple global communications. Now imagine an event 1,000 or even 1,000,000 times more powerful. A true superflare from our Sun would be an extinction-level event, not from the heat or light, but from the radiation and electromagnetic pulse that would effectively wipe out the electronic infrastructure of modern civilization and potentially scour the ozone layer, exposing all life to deadly levels of ultraviolet radiation. This frightening possibility forces us to directly confront the impact such flares would have on the habitability of exoplanets, particularly those orbiting within the so-called Goldilocks zone of active stars. A world that is otherwise perfectly positioned for liquid water could be rendered utterly sterile by the relentless blasts from its angry parent star. A superflare would not just be a light show, it would be a direct assault on a planet's atmosphere. Models suggest that a frequent barrage of such events could, over time, erode a planet's protective atmospheric layers, stripping away the nitrogen and oxygen that are essential for life as we know it. Any life that did manage to gain a foothold would also face a relentless onslaught of mutagenic radiation with each flare, potentially hindering the development of complex organisms. The search for a true Earth twin, therefore, isn't just about finding a planet of the right size at the right distance. It's also about finding it orbiting a star with a stable, gentle temperament. A star's magnetic personality is just as important as its size and temperature. This realization adds a crucial and sobering layer to our search for life elsewhere in the galaxy. It suggests that the universe might be filled with false hope planets, worlds that are technically in the habitable zone, but are periodically baked and sterilized by the fury of their suns. Our own sun's relative quiescence, its stable magnetic middle age, might be a far rarer and more precious attribute than we ever realized. It allowed life on Earth the billions of years of stable, predictable conditions it needed to evolve and thrive. The phenomenon of superflares teaches us that true habitability is a delicate and complex puzzle, where a star's temperament is a critical piece. And as we look out at the galaxy, wondering about the potential for other civilizations, we must also wonder how many of them might have had their progress abruptly reset, or never even started because their sun decided to scream. This exploration of the most violent outbursts from single stars now leads us to an even more powerful and enigmatic cosmic explosion, one that for years had no clear source, and whose origins are linked to the most magnetic and dense objects in the universe. For years, one of the most tantalizing mysteries in all of astronomy pulsed through the data streams of the world's great radio telescopes. They were called fast radio bursts, FRBs for short. These were not gentle signals, but violent, millisecond-long blasts of radio waves that would appear without warning from the depths of space, release as much energy as the sun does in days, and then vanish without a trace. Their sources were billions of light-years away, far beyond our galaxy, and they defied all explanation. Theories for their origin ranged from the cataclysmic, like merging neutron stars, to the almost unimaginable. Could they be the propulsion signatures of alien spacecraft? The mystery was so profound that it seemed we might never find an answer. Then, in April 2020, a stroke of cosmic luck occurred right in our own galactic backyard, and two profound mysteries suddenly became one. The moment of revelation centered on a known magnetar within our own galaxy called SGR 1935 plus 2154. Magnetars, as we've discussed, are already the ultimate bad boys of the stellar neighborhood, incredibly dense, spinning neutron stars with magnetic fields so powerful they could strip the information from every credit card on Earth from a distance halfway to the moon. This particular magnetar was already in a period of heightened activity, spitting out X-rays and gamma rays. Then, on April 28th, radio astronomers using the Canadian Hydrogen Intensity Mapping Experiment telescope detected something unprecedented. From the direction of SGR 1935 plus 2154 came a brilliant millisecond duration burst of radio waves. It was a flash that bore all the hallmarks of a genuine extragalactic fast radio burst, but it was happening right here in the Milky Way. Dr. Kiyoshi Masui, an astrophysicist at the Massachusetts Institute of Technology who studies FRBs, described the detection as a holy grail moment. It was the smoking gun that proved conclusively that at least some fast radio bursts are generated by magnetars. The most enigmatic signal in the cosmos had finally been linked to one of the most extreme objects we know of. This connection is far more than just solving a cosmic whodunit. It's a Rosetta Stone that allows us to start deciphering the physical language of these incredible events. The central question becomes, how can a magnetar flare produce such an intense, coherent burst of radio waves? Radio astronomers point to the insane environment just above the magnetar's surface. During a starquake or a major magnetic reconnection event, a vast cloud of plasma is ejected at relativistic speeds. This fireball then slams into the magnetar's own incredibly intense magnetic field, creating a shock wave. It is within this chaotic shock front that the magic happens. The physics suggests that something called a synchrotron maser instability can occur. Essentially, the electrons in the plasma, as they are accelerated by the shock, are forced to emit radiation in a coordinated, coherent way, much like the photons in a laser, but at radio wavelength. This process takes the tremendous magnetic energy of the flare and focuses it into a tight, brilliant beam of radio light that can be seen across the universe. It's a natural lighthouse of unimaginable power, but one that flashes only once for a fraction of a second. The properties of FRBs revealed by this and other discoveries paint a picture of astonishing diversity and power. We now know there are two broad classes, one-off repeaters and repeating FRBs. The single bursts are the most common, and they are thought to be produced by one-and-done cataclysmic events. Perhaps a magnetar flare so powerful it destroys the star's magnetic field in the process, or even the final cry of a magnetar collapsing into a black hole. The repeaters, on the other hand, are even more fascinating. These sources, like the famous FRB 1211-2 located in a dwarf galaxy 3 billion light-years away, fire off multiple bursts at irregular intervals. This implies a source that can survive its own outburst, pointing directly to the episodic, non-destructive tantrums of a magnetar. The luminosities involved are simply mind-bending. The galactic FRB from SGR 1935 plus 2154 was itself 100 times less energetic than the weakest known extragalactic FRB, which tells us that the events happening in distant galaxies must be thousands of times more powerful still true super bursts from supermagnetars. This incredible leap in understanding inevitably leads us to a humbling and reflective question. If magnetars can explain some FRBs, can they explain all of them? The sheer diversity of the signals, their energies, their repetition patterns, their locations in different types of galaxies suggests the universe might be employing more than one method to create these brilliant flashes. Some could still be the product of merging neutron stars or black holes. Others might be caused by highly magnetized white dwarfs or some other exotic object we haven't even dreamed of yet. The discovery of the galactic magnetar connection isn't the end of the FRB story. It's the end of the beginning. It gives us a firm foundation, a known physical mechanism to study up close, from which we can now explore the even wilder, more energetic events happening in the cosmic distance. It proves that the laws of physics can conspire to create natural transmitters of unbelievable power, and it makes you wonder what other impossible-seeming signals might have a similarly extreme yet natural origin. This journey into the realm of coherent radio screams from magnetic monsters perfectly sets the stage for an even more mind-warping phenomenon, where the universe itself acts as a lens, distorting and magnifying the light of distant stars in ways that feel almost like magic. Now, imagine if the universe itself offered us a magnifying glass powerful enough to see the impossible, a natural telescope of such colossal scale that it can bend the very fabric of space to bring the most distant stars into stunning, impossible focus. This is not science fiction. This is the reality of gravitational lensing, a breathtaking confirmation of Einstein's general relativity, where the gravity of a massive foreground object, like a galaxy or a cluster of galaxies, warps the space-time around it. This curvature acts like a lens, bending and focusing the light from objects far behind it, magnifying them, distorting them into arcs and rings, and sometimes even creating multiple mirror images of a single celestial source. It is one of the most powerful tools in all of astronomy, and it has allowed us to see individual stars at distances so vast they were once thought forever beyond our sight. The most stunning example of this cosmic quirk is the story of a star now known as Icarus. Its official designation is Max J1149 lensed star 1, and it holds the record for the most distant individual star ever observed. Icarus is a blue supergiant, a massive and intensely luminous star, located a staggering 9 billion light-years from Earth. Under any normal circumstances, it would be utterly invisible to every telescope ever built, a single match flame lost in the glare of a distant city. But its light had a fortuitous journey. On its way to us, it passed through a massive galaxy cluster called Max J1149 plus 2223. The immense gravity of this cluster acted as a natural zoom lens, magnifying the star's faint light by a factor of over 2,000. This incredible amplification was discovered by astronomers using the Hubble Space Telescope, who were initially studying a supernova in the same cluster when they noticed a new point of light that flared up and then faded not like a supernova, but like a variable star. They had, through a perfect and fleeting alignment, caught a glimpse of a single star from the universe's early Middle Age, Dr. Patrick Kelly, the lead researcher on the discovery, captured the wonder of the moment, stating, "You can see individual galaxies out there, but this star is at least 100 times farther away than the next individual star we can study, except for supernova explosions." The physics behind this phenomenon is both elegant and profound. Einstein's theory tells us that mass curves spacetime. A massive object doesn't just pull on other objects with gravity, it creates a dimple in the cosmic fabric. Light, always following the straightest possible path through this curved spacetime, appears to bend as it passes by. A gravitational lens can do three remarkable things to this light. It can magnify it, making faint objects appear brighter. It can distort it, stretching a distant galaxy into a long, thin arc, and it can multiply it, creating several copies of the same object arrayed around the lens. The amount of magnification depends on the precise alignment between the source, the lens, and the observer. The most dramatic effects occur in what are called caustics, regions where the light rays are focused most intensely, like the bright patterns at the bottom of a swimming pool on a sunny day. It was Icarus's passage over one of these high magnification caustics that caused its brightness to temporarily spike, allowing us to detect it. This incredible power to act as a cosmic zoom lens has been a cornerstone of the Hubble Space Telescope's legacy, particularly through programs like the Frontier Fields, which used massive galaxy clusters as natural telescopes to peer deeper into the universe than ever before. But the true revolution in this field is just beginning with the James Webb Space Telescope. JWST infrared eyes are perfectly suited to see the even more distant, more redshifted objects that Hubble could only hint at. Where Hubble gave us Icarus, Webb is expected to find entire populations of these highly magnified stars, allowing us to study the individual stars that made up the earliest galaxies. We will no longer be limited to seeing these galaxies as fuzzy blobs of combined light. We will be able to resolve their stellar makeup, understanding the types of stars that dominated the cosmic dawn and how they influenced the evolution of their nascent galaxies. The utility of lensing extends far beyond individual stars. It has been instrumental in studying some of the most energetic events in the universe. Lensed supernovae, for instance, are incredibly valuable. Because the lensing effect can create multiple images of the same supernova, each image arrives at Earth at a slightly different time due to the different path lengths the light has traveled. By measuring this time delay, astronomers can precisely calculate the expansion rate of the universe, the Hubble constant, providing a critical check on other measurement methods and helping to resolve a growing tension in cosmology. Similarly, lensed quasars, the blazingly bright cores of distant galaxies powered by supermassive black holes, have been used to map the distribution of both normal and dark matter in the foreground, lensing galaxy with exquisite detail, probing the very skeleton of the cosmos. There is a wonderful element of chance in all of this that underscores the serendipity of discovery. The detection of Icarus was a cosmic coincidence of the highest order. It required not just the precise alignment of the star, the galaxy cluster, and a single, massive star within that cluster that happened to be floating in just the right spot to act as a secondary lens, providing the final critical boost in magnification. This alignment was transient. As the universe expands and objects move, the caustic patterns shift. Icarus has since faded from view as the alignment changed, but its brief appearance provided a priceless dataset. It forces us to ponder just how much we are missing. For every one star like Icarus that flickers into view, how many billions of others remain forever hidden, their light too faint, their alignment not quite perfect. Gravitational lenses offer us fleeting, magnified windows into this hidden majority, precious glimpses of a universe teeming with stars we are only just beginning to dream of. This incredible ability to see the unseen, to study the fundamental properties of matter and light across cosmic time, naturally pushes our curiosity to the absolute limit, to wonder if some of those hidden stars might be composed of something even more strange and exotic than anything we have yet imagined. But if gravitational lensing allows us to see the unseen, it forces us to confront an even more fundamental question. What is the true nature of the matter within those distant, magnified points of light? We've pushed our understanding of density to the limit with neutron stars, objects so compressed that protons and electrons merge into a solid sea of neutrons. Yet, theoretical physics whispers of a possibility even more extreme, a state of matter so dense that the very concept of individual particles breaks down entirely. This is the hypothetical quark star, an object that shouldn't exist, a cosmic anomaly where matter crosses a final frontier and becomes something entirely new. The journey to a quark star begins where the life of a neutron star ends, during the core collapse supernova of a massive star, or in the violent aftermath of a neutron star merger. The resulting remnant is subjected to pressures and densities that dwarf anything we can conceive. In a typical neutron star, the immense gravitational force is balanced by a quantum mechanical principle known as neutron degeneracy pressure, which prevents the neutrons from cramming any closer together. But for the most massive remnants, this pressure might not be enough. Theorists like Dr. Fridolin Weber, a physicist who specializes in these exotic states, suggest that under this incredible crush, the neutrons themselves might shatter. Their fundamental components, the quarks held prisoner within them by the strong nuclear force, could break free in a process called deconfinement. The entire star would then transition from a solid of neutrons into a vast, ultra-dense soup of free-flowing up, down, and strange quarks, a form of matter known as quark-gluon plasma. It would be a star with no atomic structure left at all, a perfect, seamless ocean of the universe's most basic building blocks. How would we ever recognize such an object? Its signatures would be subtle yet profound. A quark star would be even smaller and denser than a neutron star of the same mass. Imagine an object with the mass of our entire sun, but compressed into a sphere only 10 kilometers across, the size of a small city. A quark star might squeeze that same mass into a ball just a few kilometers smaller in radius. This tiny difference has huge implications. Its surface gravity would be even more intense, and its cooling curve, the way its temperature drops over time, would be dramatically different. The direct Urca process, a hyper-efficient neutrino emission mechanism that only operates in quark matter, would allow a quark star to cool from a searing trillion degrees to a cold cinder in a matter of centuries, far faster than a neutron star. Spotting this rapid temperature drop could be the key piece of evidence, but it requires catching a newborn star remnant at just the right moment. The greatest challenge in this hunt is that from a distance, a quark star would be a master of disguise. It would still have the same mass, spin, and often the same powerful magnetic fields as a neutron star. It would still pulse as a pulsar or flare as a magnetar. To our telescopes, it would look and behave almost identically to its more conventional cousin. The tiny differences in radius and cooling are incredibly difficult to measure across light years of space. This is why every candidate quark star is shrouded in controversy. The most famous of these is RxJ 1856.5-3754, a lonely stellar remnant floating about 400 light-years away. Early X-ray observations suggested its radius was impossibly small for a neutron star, pointing toward a more exotic composition. The media buzzed with the possibility of the first quark star. However, later, more precise observations introduced doubt. Some analyses suggested its surface might be hotter in some spots than others, or that its tiny size could be explained by an unusual atmosphere of iron plasma pulled into a thin haze by immense gravity. To this day, RxJ 1856 remains an enigma, a tantalizing maybe that keeps the door to this radical idea firmly open. Our best hope for finally settling the debate may not come from traditional astronomy, but from the new era of gravitational wave science. When two neutron stars spiral together and collide, they create ripples in spacetime that observatories like LIGO and Virgo can detect. The precise shape of these gravitational wave signals is exquisitely sensitive to the internal structure of the merging objects. A collision between two standard neutron stars would produce one signature, but if one or both of those objects were actually quark stars, the signal would be different. The point of merger might happen at a different frequency, and the resulting remnant might collapse into a black hole almost instantly, or it might persist for a fraction of a second longer as a single, gigantic quark star before its own weight consumed it. These tiny deviations in the gravitational wave chirp are the fingerprints of phase transitions, the moment matter itself changes its state from hadronic to quark matter. Each new neutron star merger detected is a potential test, a chance to hear the universe itself whisper the answer to this profound question. Pondering the existence of quark stars forces us to confront the very nature of reality. What does it mean for matter to be pushed to its absolute limit? If quarks can be set free from their nuclear prisons, what other states of matter might be possible in the hearts of these incredible objects? Could there be color superconductors where quarks pair up and flow without resistance, or strange matter that is actually the universe's true ground state? These aren't just abstract puzzles. They are questions that strike at the heart of the standard model of particle physics. By studying the largest objects in the universe, we are indirectly probing the smallest, using stars as colossal laboratories to understand the forces that govern quarks and gluons. This incredible convergence of cosmology and particle physics reveals a universe that is far stranger and more wonderful than we could have ever imagined, filled with matter in forms we are only beginning to dream of. Now let's turn from the exotic states of matter within quark stars to the equally bizarre chemistry on the surfaces of certain stars, where the universe seems to be conducting elemental experiments that defy all standard recipes. Imagine pointing a spectroscope at a seemingly ordinary star and finding its light fingerprint isn't just unusual, it's utterly incomprehensible, showing lines for elements that shouldn't be there in such abundance or even at all. These aren't just minor chemical quirks, They are profound cosmic anomalies written in the language of atomic absorption, each one a cryptic message about the most violent and rare events in the cosmos. The discovery of these chemically peculiar stars is a direct result of our most ambitious sky surveys. Projects like the Sloan Digital Sky Survey have collected spectra for millions of stars, creating a vast chemical census of the Milky Way. Astronomers use sophisticated software to automatically analyze these spectra, measuring the depth of absorption lines to determine the precise abundance of dozens of elements in a star's atmosphere. It's like taking a core sample from a tree ring, but on a galactic scale. Most stars follow predictable patterns. They have compositions that reflect the interstellar gas from which they formed. But a tiny fraction, less than 1%, stand out as radical outliers. Their spectra reveal extreme overabundances of specific rare Earth elements, shocking depletions of common ones like lithium, or, most mysteriously, the presence of radioactive elements with half-lives so short they must have been forged just before the star was born. Dr. Anna Frebel, a renowned astrophysicist at MIT who hunts for these ancient chemical fossils, often says, "The atmosphere of a star is a time capsule. It records the composition of the gas cloud it formed from, and when that composition is weird, it's telling us a story about a very special event that happened right next door, right before that star lit up." So what is the significance of these bizarre chemical signatures? They are nothing less than direct forensic evidence of the universe's most catastrophic and elemental forging processes. The elements that make up our world weren't all created in the same way. Common elements like carbon and oxygen are cooked steadily in the cores of ordinary stars. But the heavier elements, the gold in your jewelry, the uranium in nuclear reactors, the europium in your phone's screen require something far more violent. Chemically peculiar stars are the cosmic signposts pointing to these events. An extreme overabundance of elements like gold, platinum, and europium is the classic signature of the rapid neutron capture process, or R process. This requires an environment flooded with free neutrons, where atomic nuclei are bombarded and built up into heavy elements in a matter of seconds. The only events thought to produce such conditions are the cataclysmic mergers of two neutron stars or certain types of rare supernova. When we find a star with a huge enhancement of R process elements, we are effectively looking at the debris field from one of these ancient cosmic explosions, frozen in time within that star's atmosphere. To understand this, we need to distinguish between the two main cosmic forges. The R process is the rapid one, happening in the chaotic seconds during a neutron-star merger. The S process, or slow neutron capture process, is its more sedate cousin. This happens over thousands of years inside aging giant stars, where neutrons are added to nuclei at a slower pace, producing a different pattern of elements like barium and lead. By reading the specific ratios of elements in a peculiar star, the amount of europium compared to iron, or strontium compared to barium, astronomers can perform cosmic archaeology, determining not just that a dramatic event happened, but exactly what kind of event it was. It's like analyzing the chemical residue at a crime scene to determine the type of explosive that was used. No star exemplifies this mystery more than the legendary Pulsar star, also known as HD 101065. Located over 400 light-years away, this star is the undisputed king of chemical weirdness. Its spectrum is a chaotic jungle gym of absorption lines, many of which were initially unidentifiable. When scientists finally decoded them, the results were staggering. Pulsar star contains enormous amounts of rare earth elements like holmium, lutetium, and promethium. But the real shock was the presence of short-lived radioactive elements like plutonium, einsteinium, and curium. These are elements with half-lives measured in mere years, decades, or centuries. They cannot have been part of the original gas cloud that formed the star billions of years ago. They would have decayed into other elements eons ago. Their presence implies a continuous or very recent production mechanism right in the star's vicinity. The leading theories are as wild as the data itself. Some suggest the star has a highly magnetic neutron star companion that is bombarding it with radiation, literally transmuting existing elements into these radioactive oddities. Others propose even more exotic ideas, like the presence of islands of stability for super-heavy elements unknown on Earth that are slowly decaying and producing the observed isotopes. Przybylski's star remains a beautiful and unsolved puzzle, a reminder that our periodic table might only be a small part of the cosmic whole. The story of these stars is also the story of our galaxy's own evolution, a field known as galactic chemical evolution. Imagine the early Milky Way as a vast, pristine sea of hydrogen and helium. The first supernova began to pollute this sea with the first heavy elements carbon, oxygen, magnesium. As the galaxy evolved, different events occurred in different places. A neutron-star merger might seed a local cloud with R-process elements. A Type Ia supernova might inject it with iron and silicon. Then, a new generation of stars would form from this now enriched gas, locking that specific chemical fingerprint into their atmospheres. By mapping the locations and compositions of chemically peculiar stars across the Milky Way, astronomers can literally chart the history of these explosive events. Stars with certain signatures tend to be found in the older, thicker disk of the galaxy, telling us that R-process events have been occurring for billions of years. Others are found in specific streams or clusters, revealing the chemical ancestry of those groups. It's a grand galactic genealogy written in starlight. There's a compelling anecdote from the painstaking work of modeling these stellar atmospheres. The complex calculations required to interpret a star's spectrum involve millions of lines of code and rely on atomic data measured in laboratories here on Earth. For the most bizarre stars, like Przybylski's, astronomers often find themselves waiting for nuclear physicists to first measure the properties of an obscure element in a particle accelerator before they can even identify a line in their spectrum. This intimate collaboration between the scientists who study the biggest things in the universe and those who study the smallest is a powerful testament to how interconnected our quest for knowledge truly is. They are literally writing the key to decode the universe together. This incredible journey from the first elements to the complex chemical tapestry we see today forces a profound and personal reflection. Every heavy atom in our bodies was forged in the heart of a dying star or in the unimaginable violence of a neutron-star collision. We are not just living in the universe, we are literal products of its most dramatic and creative processes. The calcium in our bones, the iron in our blood, and the iodine in our thyroid were all created in these cosmic cataclysms and then scattered across space, eventually finding their way into the nebula that formed our sun and our planet. When we study a chemically peculiar star, we are not just looking at a distant curiosity. We are looking at a relative, a cousin that formed from a cloud seeded by the same galactic events that ultimately made us possible. This deep connection between the violent history of the cosmos and the very composition of our own bodies makes the next possibility all the more captivating. The idea that life itself might find a way to thrive in environments we would consider chemically bizarre. But what if the very concept of a habitable zone is far more flexible and strange than we ever imagined? We have spent decades searching for planets orbiting other stars, meticulously mapping the regions where liquid water could exist on a world basking in the warmth of its sun. But this entire paradigm assumes the planet has a sun at all. Now, let's venture into the deepest, coldest voids between the stars, to a class of worlds that have been utterly forgotten by their parent stars, cast adrift to wander the galaxy alone. These are rogue planets, and the possibility that they could harbor life forces us to rewrite the textbook on what makes a world alive. The traditional image of a rogue planet is one of perpetual, frozen night, a barren ball of rock and ice, its surface locked in an eternal, deep freeze darkness, its atmosphere collapsed into a global glacier. For most of these orphans, this bleak fate is undoubtedly true. But astrophysics reveals a more nuanced and fascinating picture. Imagine a rogue planet that is a gas giant, like a young Jupiter, freshly ejected from its stellar nursery. Its interior would still be glowing with the fierce, residual heat of its formation, a primal warmth that could take billions of years to dissipate into space. Now imagine that this giant world has a large, rocky moon. From the perspective of that moon, the gas giant is not a planet, it is a sun. It would hang in the perpetually black sky not as a point of light, but as a vast, dimly glowing orb, radiating a dull crimson heat. This creates a pocket of possibility, a substellar habitable zone where the moon's surface could be warmed not by distant starlight, but by the gentle infrared glow of its planetary host. The challenges to life in such an environment are, of course, monumental. The primary issue is energy. Without a bright, central star, the driving force of photosynthesis is off the table. There is no sunlight to power a classic food chain with plants at its base. Astrobiologists like Dr. Manasvi Lingam have explored the alternative energy sources that could sustain a biosphere in this profound darkness. The most promising candidate is chemosynthesis, the same process that supports entire ecosystems on Earth at the bottom of the ocean, clustered around hydrothermal vents. There, bacteria derive energy not from the sun, but from chemicals spewed forth from the Earth's interior, like hydrogen sulfide. These bacteria form the base of a food web that includes giant tube worms, blind shrimp, and unique species of crabs. On a rogue moon, the energy for such a system could come from the tidal forces exerted by the gas giant. As the moon orbits, the giant planet's gravity would flex and stretch its interior, generating intense geothermal heat through friction. This could power volcanic activity on the seafloor, creating hydrothermal vents that would serve as natural reactors, churning out the chemical energy needed to fuel life. The stability of such a system is its own fascinating puzzle. A planet-star system is dynamic. Stars age, brighten, and eventually die, shifting their habitable zones over time. But a rogue planet-moon system is arguably more stable. The heat source, the slow, radioactive decay and gravitational contraction within the gas giant fades over billions of years, but it does so in a far more gradual and predictable manner than a star's life cycle. There are no solar flares, no variable stellar activity. The environment, while extreme, could be incredibly consistent for eons, offering life a long, quiet, and stable timeline in which to arise and evolve in its own unique way. The climate would be global and temperate, dictated entirely by internal geology and the constant, faint warmth from below and from the giant in the sky, with no risky dependence on a temperamental star. We can already use sophisticated computer simulations to paint a picture of what the atmosphere of such a world might be like. Models suggest that a thick atmosphere, rich in greenhouse gases like hydrogen, could act as an insulating blanket, trapping the internal heat and preventing it from radiating too quickly into space. This could maintain surface temperatures above the freezing point of water, even in the utter absence of starlight. The sky would not be blue, but a perpetual, deep twilight. Weather patterns would be driven by the heat gradient between the warm surface and the cold of space, potentially creating slow, global wind systems and precipitation, perhaps not of water, but of other compounds like ammonia or hydrocarbons, depending on the chemistry of the world. The ultimate question, of course, is how we could ever hope to find such a hidden, dark ecosystem. The answer lies in the next generation of telescopes. The James Webb Space Telescope and future observatories like the Habitable Worlds Observatory will be equipped to study the atmospheres of exoplanets by analyzing the starlight that filters through them. For a rogue planet with a moon, the technique would be different but similar. If such a world were to pass fortuitously in front of a more distant background star, its atmosphere would be briefly backlit. Our telescopes could capture that transmitted light and perform spectroscopy on it, looking for the telltale biosignatures, not just oxygen, which requires photosynthesis, but chemical imbalances that are hard to explain without biology. A simultaneous detection of methane and oxygen, or certain complex organic molecules, would be a screaming siren in the data, a potential sign of life processes operating in complete isolation from any star. This concept forces a profound shift in our perspective on life's tenacity. It suggests that habitable real estate in the galaxy might be far more abundant than we thought, existing not just in the narrow Goldilocks rings around stars, but in the vast dark spaces between them. It expands the potential cradle of life from a specific orbital distance to any world with a sufficient internal heat source and the right chemistry. How many of these dark, nomadic worlds are drifting through the void, potentially carrying their own hidden, bioluminescent oceans beneath icy shells? The possibility is both humbling and exhilarating, suggesting that life may find a way in environments we would consider utterly hostile. And if life can thrive in such impossible places, clinging to the faint warmth of a rogue giant, then what other feats of cosmic engineering might be possible for a sufficiently advanced intelligence? Now let's take a leap from the cold, dark wanderers to perhaps the most ambitious theoretical construct ever imagined, a civilization so advanced it doesn't just inhabit a world, but re-engineers an entire star system to suit its boundless energy needs. This is the awe-inspiring concept of the Dyson sphere, a megastructure of almost incomprehensible scale, representing a technological achievement that would fundamentally alter the appearance of a star from light years away. The idea was first popularized by physicist Freeman Dyson in 1960, though he was quick to credit the earlier science fiction author Olaf Stapledon as the true inspiration. Dyson's genius was not in designing a blueprint, but in realizing that any civilization reaching a certain level of technological maturity would inevitably face energy limitations on its home planet. The logical solution to capture the entire energy output of its parent star, he argued that such a project would be not just visible, but glaringly obvious across interstellar distances because the laws of thermodynamics are unforgiving. All that captured energy, after being used for computation, industry, or whatever unimaginable purposes an advanced culture might have, must eventually be wasted as heat. This waste heat would be radiated away as infrared light, making a star surrounded by a Dyson structure appear as a brilliant, anomalous pinprick of infrared radiation against the cold backdrop of space, with little or no visible light to accompany it. The ongoing scientific search for these cosmic engineering projects is a fascinating exercise in balancing open-minded speculation with rigorous skepticism. Initiatives like Project Hephaestus, the Glimpsing Heat from Alien Technologies Survey, and others are not wild hunts for little green men. They are systematic, data-driven efforts to scour infrared sky surveys from telescopes like NAS, a wide-field infrared survey explorer, and the Japanese Icarus satellite for exactly this kind of anomalous signature. Astronomers like Jason Wright at Penn State University, a leading figure in this field, often emphasize this careful balance. He notes, "The hypothesis that an astronomical anomaly could be due to aliens must always be the last one you consider, but that doesn't mean you shouldn't consider it at all. You first have to rule out all the natural, often complex astrophysics that could mimic the signal. It's a process of elimination where the most exciting answer is also the least probable." This methodical approach ensures the field remains scientifically credible, treating the search for Dyson spheres not as a quest for proof, but as a process of excluding all known natural explanations for bizarre infrared sources. It's crucial to understand that a Dyson sphere is rarely imagined as a single, solid, rigid shell, a concept fraught with engineering impossibilities due to immense gravitational stresses and material strength limitations. Instead, theorists envision several more plausible configurations. The most likely is the Dyson swarm, a vast collection of individual energy-capturing satellites, think mirrors, solar panels, or habitats, each in independent orbit around the star, collectively forming a loose, thick cloud that intercepts a large fraction of the starlight. A more advanced version might be a Dyson bubble, which would use statite satellites that hold their position not with orbital motion, but with radiation pressure from the star itself, acting like solar sails. The classic solid shell remains a staple of science fiction, but it represents a level of control over matter and gravity that may forever remain in the realm of fantasy. Each type would have a different observational signature. A complete shell would block all visible light, leaving only the infrared glow. A partial swarm, however, would cause irregular and aperiodic dimming of the star as different clusters of satellites transit across its face, and would still emit a strong infrared signal from the absorbed and re-radiated energy. The most famous real-world candidate that fueled this very discussion is the star we've already met, KIC 8462852, or Boyajian star. Its bizarre, deep, and irregular dimming patterns initially led some to half-jokingly suggest it was surrounded by a partially constructed Dyson swarm. However, as we discussed, intense follow-up study revealed that the dimming was wavelength-dependent, stronger in blue light than in red, a clear signature of scattering by fine dust, not the light blocking of solid megastructures. Furthermore, no significant infrared excess was found around the star. If a Dyson swarm were active, the star should be blazing in the infrared. Its absence was a major point against the alien megastructure hypothesis. Boyajian's star now serves as a perfect case study for how natural phenomena can brilliantly mimic artificial ones, and how the scientific process diligently works to unravel them. It teaches us that the universe is often stranger than our fiction, producing incredible natural puzzles that need no alien explanation. The original inspiration for this entire idea came from a place of profound curiosity. Freeman Dyson was not an avid science fiction reader, but he credited a passage in Olaf Stapledon's 1937 novel, Star Maker, with planting the seed. In it, Stapledon describes a galaxy where advanced civilizations eventually construct a web of light-trapping structures around their stars, creating a dark universe punctuated by these engineered infrared suns. Dyson saw in this not just a neat story, but a serious scientific prediction. He realized that if such civilizations existed, this would be their most detectable, galaxy-changing signature. He was less interested in the engineering than in the astronomy. He gave scientists a concrete, empirical thing to look for. This elegant marriage of a science fiction concept with hard thermodynamic prediction is a beautiful example of how imaginative thought experiments can directly guide real scientific inquiry. One cannot help but try to stretch the imagination to its limit when considering a civilization capable of such a feat. What would it mean to harness the total power of a star? The energy output is staggering. Our sun emits roughly 380 sextillion watts every second. A civilization controlling that could compute, build, and explore on a scale we can barely dream of. Perhaps they would use the energy to power supercomputers for vast simulated realities, or to accelerate starships to near light speed, or to literally rearrange the planets in their system. The construction project itself implies a mastery of nanotechnology, self-replicating machinery, and orbital mechanics that would make our greatest engineering efforts, like the International Space Station, look like a child's sandcastle. The very act would mark a species transition from a planetary society to a stellar one, becoming a truly eternal entity, immune to the eventual death of its home world and secure for billions of years around the steady glow of its star. This contemplation of ultimate technological power perfectly sets the stage for our final frontier, because if we can dream of finding the artifacts of such civilizations, then the future of astronomy must hold the tools to discover not just stranger stars but stranger constructions. We have spent our journey marveling at the cosmic rule breakers we have already found, from zombie stars to diamond-forging giants. But if history has taught us anything, it is that the universe's capacity for wonder far exceeds our current imagination. We are standing on the brink of a new golden age of discovery, an era where our tools will finally match our ambition, allowing us to peer into realms of space and time we have so far only theorized. This is not the end of our exploration. It is the very beginning of the next chapter, powered by a new generation of observatories so advanced they feel like they were pulled from the pages of science fiction. Leading this charge is the James Webb Space Telescope, an engineering marvel that has already begun rewriting the textbooks, but JWST is just the first scout. It will soon be joined by colossal ground-based giants like the extremely large telescope in Chile, with a primary mirror an astonishing 39 meters across, and the Square Kilometer Array, a radio telescope network so sensitive it could detect an airport radar on a planet dozens of light years away. Each of these instruments is designed to see the universe in a different light, from the piercing infrared eyes of Webb that can see through cosmic dust, to the radio ears of the SKA that will listen to the faint whispers of atomic hydrogen from the dawn of time. Dr. John Mather, Webb's senior project scientist, often speaks of this not as one discovery, but as a new way of seeing. He says we are opening up a window to an entirely new universe, one that has been hidden from us until now. The scientific goals of these titans are as breathtaking as their specifications. One of the most profound is the hunt for the first starlight, the mythical population 3 stars. These are the universe's first giants, made only of hydrogen and helium, whose brilliant lives and violent deaths seeded the cosmos with the first heavy elements. JWST is already probing the deepest infrared fields, looking for the unique chemical fingerprints of these pristine stars in the light of the most distant quasars. The ELT, with its incredible light-gathering power, will be able to directly detect the supernova of these first stars, watching as they literally light up the dark, early universe for the very first time. It is a chance to witness the moment of cosmic enlightenment, the end of the Dark Ages and the beginning of everything we know. Closer to home, these telescopes will transform exoplanet science from simple detection into detailed characterization. The advanced coronagraphs on the ELT and the next-generation space-based Habitable Worlds Observatory will allow us to do the seemingly impossible: directly image an Earth-sized planet orbiting a sun-like star. We will not just see it as a pixel of light. We will be able to split its light into a spectrum, searching for the telltale biosignatures of life, the simultaneous presence of oxygen and methane, or the subtle glow of vegetation on a continental scale. We will be able to study the weather on these distant worlds, mapping clouds and storms on gas giants, and perhaps even detecting surface features on rocky twins. This moves our question from "Are we alone?" to "What does life on that world look like?" Furthermore, these observatories will bring distant stars into stunning focus, resolving their surfaces in ways we never thought possible. The technique of optical interferometry, combining the light of multiple telescopes, will effectively give us a mirror the size of the entire Earth. This could allow us to map star spots on the surfaces of distant suns, watch in real time as a supergiant star pulsates, and even trace the flow of material in the accretion disks around newborn stars, witnessing the very birth of solar systems. We might finally get a clear view of the mysterious surroundings of black holes and neutron stars, understanding the physics of these extreme environments by watching how matter behaves just moments before it is lost forever. One can run vivid simulations of what the first JWST images of the early universe might reveal. Instead of the faint, red smudges we see from Hubble, Webb's infrared vision shows these same objects as structured, clumpy, infant galaxies, actively devouring gas and furiously forming their first generations of stars. The data is not just a picture, it is a movie trailer for the formation of our own Milky Way. The ELT could take this even further, providing the spectral data to measure the motions of gas within these primeval galaxies, revealing the initial buildup of the supermassive black holes that will one day dominate their centers. This incredible future forces a humbling and exciting question: what mysteries remain that we haven't even thought to ask? Every time humanity has built a bigger telescope, we have discovered something so fundamentally new that it shattered our previous understanding. Galileo's telescope revealed moons around Jupiter, proving not everything orbited the Earth. Hubble's deep field revealed a universe filled with billions of galaxies. What will the JWST, the ELT, and the SKA reveal that will force us to tear up our current textbooks? Will we find evidence of physics beyond the standard model in the remnants of the first stars? Will we discover a stellar phenomenon so bizarre it makes our previous anomalies look mundane? The greatest discovery may not be the one we are searching for, but the one that finds us, the signal in the data that is so strange it forces a complete rethink of our place in the cosmos. And so our journey through the cosmos's most magnificent rule breakers draws to a close. We've stood in awe of zombie stars that cheat death, witnessed hypervelocity runaways fleeing their galaxies, and marveled at suns burning in the violent heart of chaos. We've encountered diamond-forging carbon stars, vampire pulsars that devour their companions, and hybrid stellar monsters with neutron hearts. We've seen stars older than the universe itself, theoretical giants powered by dark matter, and failed stars so cold they blur the line between sun and planet. From the terrifying magnetic fury of Magnetars to the stolen youth of blue stragglers, from oxygen-shrouded white dwarfs to pulsating stars with mysterious heartbeats, each anomaly has been a profound lesson in cosmic humility. The overarching theme that binds these celestial marvels together is a beautiful and powerful one. The universe is not a static museum of predictable objects following a simple set of rules. It is a dynamic, creative, and often chaotic laboratory, constantly conducting experiments in physics under conditions we can scarcely replicate. Every time we think we have it all figured out, the cosmos delivers another surprise, a star that spins too fast, a chemical signature that makes no sense, a flicker of light that defies all classification. These aren't mere curiosities, they are the cutting edge of discovery, each one a crack in the facade of our understanding, letting in a little more light on the true, magnificent complexity of nature. They force us to question, to innovate, and to admit that for all we have learned, we have only just begun to scratch the surface. This relentless pursuit of understanding, driven by both curiosity and wonder, is what propels science forward. It underscores the vital importance of continued observation with ever more powerful telescopes and the development of bolder, more imaginative theoretical models. As Carl Sagan so eloquently reminded us, somewhere something incredible is waiting to be known. This isn't just a poetic sentiment, it is a fundamental truth of exploration. It is the engine that has driven us from the first time a human looked up at the night sky in wonder to the moment we pointed the James Webb Space Telescope at a patch of darkness and found a universe teeming with unexpected glory. The search is never over. Each answered question begets a dozen new ones, and in that endless, glorious cycle of mystery and discovery, we find our purpose as explorers. Now we pass that sense of wonder on to you. The next time you find yourself under a clear night sky, look up. Let your gaze wander from star to star, and remember that each pinprick of light is not just a distant sun, but a potential world of mystery. It could be a variable star taking its last erratic breaths, a magnetar storing unimaginable energy, or a contact binary sharing its atmosphere in a cosmic dance. That sky is alive with drama and discovery, a story unfolding in real time across unimaginable distances. Let that knowledge change your perspective forever. The adventure doesn't end here. This is just one chapter in an ongoing story of cosmic revelation. If you've enjoyed this tour of the universe's strangest stars, make sure to subscribe to the channel so you don't miss our next journey into the mysteries of space. Share this video with a friend who gazes at the stars with the same sense of wonder, and let us know in the comments below which of these celestial anomalies captured your imagination the most. Is it the terrifying power of a magnetar, the eerie paradox of a zombie star, or the beautiful mystery of Boyajian's star? We love hearing from you.